Why does the creation of iron mark the beginning of a massive star's end? How does a star's brilliance come at the cost of its short life? What can the final days of a giant star teach us about cycles of creation and collapse? In the hushed darkness between the stars, a giant sun is living out its final days. Far from any planet or bustling system, it glows softly in the cosmic night, a massive star nearing the end of its long life. It is a solitary beacon in a quiet corner of its galaxy, with only the distant lights of other stars twinkling far away. For millions of years, it has shone brilliantly, pouring its light and warmth into the void. But now, its fuel is nearly spent, and a quiet change has begun deep within its core. This star is a behemoth, many times the mass of our sun. Once, in its youth, it burned a brilliant bluish-white, fiercely hot and radiant. Now, in its old age, it has swelled into a red supergiant, larger, cooler, and gentler in its light. Its radius is so vast that it would dwarf our entire solar system. A beam of light would take more than an hour to cross from one side of the star to the other. The star's outer layers have expanded outward, drifting like a tenuous veil around a fiercely burning core. The star has been gently shedding gas into space for thousands of years, creating a faint halo of stardust around its periphery. Despite its immense power, its surface glows with a soft, reddish hue, a steady and calm light against the blackness of space. It is truly one of the giants of its galaxy, enormous and majestic even in its old age. If we could voyage close to this star, the sight would be astonishing. From afar, it appears as a ruby-red point of light, but as we draw nearer, it swells into an immense crimson sphere hanging in the void. Soon it fills our view, an awe-inspiring ocean of red light stretching out before us. Its light is gentle at a distance, but up close, it would bathe everything in a warm, reddish glow. The star's surface, though cooler than many stars, still shines with a deep, steady light, and we would see vast patches and swirls as currents of hot gas move across its face. In every direction around the star is the emptiness of space, making the star's presence all the more profound and majestic. Such massive stars live fast and die young in cosmic terms. They blaze through their nuclear fuel with incredible intensity, shining far more brilliantly than smaller, steadier stars. This brilliance comes at a cost. Instead of the tens of billions of years that a star like our sun might enjoy, this giant has lasted only a few million years, a mere blink of an eye in cosmic time. It has been a brief but magnificent existence, a quick crescendo of energy and light that now approaches its final refrain. Deep inside, however, this star is no longer calm. Like the final movement of a long symphony, processes in the core are reaching a dramatic crescendo. For ages, the star has balanced gravity's pull with the power of fusion in its core, forging heavier and heavier elements from lighter ones. Hydrogen became helium. Helium fused into carbon and oxygen. Carbon created neon and magnesium, and so on. Each stage released energy and sustained the star, a series of nuclear melodies that kept it alive. Layer upon layer of spent fuel built up in shells around the core, like the rings of a mighty tree marking the passage of time, or like the layered harmonies of an orchestra building toward a finale. Now, at last, the star's core has created the element iron, and this changes everything. Iron is unique. Unlike all the fuels that came before it, fusing iron doesn't give off energy. Instead, it greedily absorbs energy. In the star's core, the creation of iron is like a final note held too long, fading into silence. No more energy can be drawn from fusion to hold up the star's immense weight. It is as if the star has reached a dead end in its long journey of burning. Without the outward push of new energy, the balance that supported the star begins to crumble. Gravity, which the star fought against for eons, now starts to tip the scales in its favour. A quiet crisis is brewing at the centre of the giant, a catastrophe unfolding in slow motion deep within, invisible from outside. In the star's final moments, a quiet tension builds. The iron-filled core can no longer sustain the crushing pressure from above. Yet, just outside that core, the star's remaining fuel burns furiously in concentric shells, like layers of an onion, fusing lighter elements in a last desperate effort to hold off collapse. One by one, these shells exhaust their fuel. As each layer burns out, its spent ash, new iron, and other elements falls onto the core, adding to the core's growing weight. The process accelerates, running faster and faster, as if the star is racing through its final notes, and each note is shorter than the last. It is a frantic race against gravity, one the star can only delay for a moment. Gravity is patiently waiting to make its move. The star's colossal core is reaching its breaking point. At this stage, the core has shrunk to roughly the size of a planet like Earth, yet it contains nearly the mass of the Sun. In these final instants, the temperature at the center has soared to unimaginable heights, and the core begins to contract under its own immense gravity. There is a sense of deep anticipation, as if the star itself is holding its breath. Outwardly, there are almost no signs of the impending catastrophe, perhaps just a subtle flicker in the star's light, or a faint tremble across its surface. To any distant observer, the star still appears placid and unchanging, a crimson globe quietly shining. But inside, the usual order of matter is about to break down. The very atoms are on the brink of an extraordinary transformation, poised at the edge of a violent event. This is the quiet before the cosmic storm. From the outside, the giant star betrays almost nothing of the turmoil within. It glows serenely as it always has, a tranquil crimson sphere against the black of space. Yet deep inside, an irreversible chain of events has been set in motion. It is a moment of profound stillness, the final calm that comes just before everything changes. It happens suddenly, though in truth this finale has been long in the making. After millions of years of shining, the star's end now comes in a mere instant. In less than a heartbeat, the star's core can no longer bear the burden upon it. Like a drumbeat that finally stops, the support holding up the core vanishes. Gravity comes rushing in, and the core plummets inward, collapsing tighter and tighter at phenomenal speed. All the star's brilliance and all its fury now converge upon that imploding heart, ready to unleash one final, monumental outburst. The dying star's final symphony is about to reach its ultimate crescendo. In an almost unimaginable instant, the core implodes. The very heart of the star, which was once thousands of kilometers across, is crushed down with staggering force to a sphere only a few tens of kilometers wide. Protons and electrons, normally kept apart, are slammed together by the furious collapse. They merge into neutrons, releasing a flood of ghostly neutrinos that instantly begin streaming out into space. In that brief moment, more of these neutrinos are unleashed than in all the millions of years before. All of this occurs in complete silence, deep within the star's center, hidden from any outside observer. As the core collapses to an ultra-dense state, a new force suddenly rises to halt its fall. The neutrons, those newly formed particles packed together tighter than ever, strongly resist further compression. In that brief instant, the core's density becomes enormous, akin to the density of an atomic nucleus. All the collapsing material slams into this neutron barrier, and the implosion screeches to a halt, as if hitting an invisible wall. For a tiny fraction of a second, the core even bounces outward slightly. This tiny rebound sends a powerful shockwave rippling outward through the layers of the star. That shockwave races outward from the core, blasting through the star's layers at incredible speed. In mere moments, the star's vast outer shell is being ripped away. The energy of the implosion, now rebounding outward, propels the star's gases violently into space. The star is literally torn apart from within. A brilliant flash illuminates the cosmic darkness as the star's outer layers are hurled off, forming a rapidly expanding, glowing cloud. This is the supernova, the star's grand finale, a titanic explosion that marks the end of the old star and the beginning of something new. In mere seconds, a star that existed for ages has been unmade, its material blown into the cosmos. For a brief time, the dying star becomes one of the brightest beacons in the universe. It outshines entire galaxies, pouring out more light than billions of suns combined. Yet the power it releases is beyond imagination. In seconds, this dying star emits more energy than a smaller star, like our Sun, could in 10 billion years. And for all its brilliance, this cosmic fireworks display is utterly silent. In the vacuum of space, there is no sound, so the star's catastrophic end arrives quietly. Only light and those ghostly neutrinos rushing outward mark the event. To a distant observer, it appears as a sudden blossom of light in the sky, blooming quickly and then slowly fading away, all without a sound. Perhaps, on a faraway world orbiting a distant sun, the death of this star would be witnessed as a strange new light in the sky. Night after night, an unfamiliar star would gleam where once there was darkness, reaching its peak brilliance and then gradually fading away. To those distant observers, it would be a silent spectacle, a cosmic firework that blossomed without a sound. After a time, the new star would disappear from their sky, leaving only mystery behind, its brief appearance and quiet exit remembered in wonder. As the glare of the supernova begins to fade, the aftermath slowly reveals itself. Where once the star's core lay, there is now only a tiny, immensely dense object left behind. All around it, the star's former outer layers continue to surge outward, expanding as a nebula of glowing debris. But at the very heart of that expanding cloud lies something new and extraordinary, a newborn neutron star. This is the small, surviving core of the once mighty star, now laid bare to the cosmos for the first time. In the span of less than a heartbeat, the core's collapse and rebirth have taken place. A massive star has died, and in its death, it has given birth to one of the strangest objects in the cosmos. The neutron star that remains is incredibly small compared to the original star, no larger than a city in diameter, yet it contains nearly all the mass of our Sun. It's as if all the star's essence has been compressed into a sphere only a few miles across. This tiny remnant now sits quietly at the center of the expanding wreckage, a quiet guardian of the chaos it created. This neutron star is a cosmic paradox, a titan in mass, but a dwarf in size. Imagine something as heavy as the Sun crushed into a sphere only about 10 miles, or 16 kilometers, across. It's as if a mountain of material were squeezed into the size of a small town. The density is truly beyond comprehension. Just a single teaspoonful of neutron star matter would weigh billions of tons on Earth, more than a mountain. All of that weight is packed into a ball so small we could walk its circumference in an afternoon, if we somehow could survive on its surface. Gravity on the surface of this tiny star is unimaginably strong. If an object were to fall onto the neutron star, it would slam into the surface at a significant fraction of the speed of light. The pull is so extreme that even a small pebble dropped from a short height would strike with a tremendous release of energy, far beyond anything we could ever create on Earth. The neutron star's gravity is so intense that it even warps the space around it, bending the path of light that passes nearby. Even a mountain-sized bump on its surface would be flattened in an instant by gravity's pull. Yet all of this occurs quietly and invisibly in the depths of space. There is no roar, no crash that anyone can hear. Only perhaps a burst of high-energy light might signal such an event to distant observers. The material that makes up this strange little star is unlike anything found on Earth. Under such crushing pressure, matter is essentially a vast sea of neutrons. You can imagine it as a single gigantic atomic nucleus, an enormous ball of subatomic particles pressed tightly together. The neutron star's crust might be a thin layer of ordinary atoms, perhaps mostly iron, but even those are squeezed into exotic forms. Beneath that thin crust, the distinction between individual atoms disappears, replaced by an ultra-dense state of matter. It is matter at the edge of physics, perhaps the strangest form of matter in the universe, where atoms as we know them cannot survive, having been transformed into something more primordial. This newly formed neutron star is not only dense and heavy, it's also likely spinning very fast. As the core collapsed, it conserved its angular momentum, like a figure skater pulling in their arms to spin faster. What was once a leisurely rotation of the giant star has become a rapid whirl. The neutron star could be spinning many times per second, turning relentlessly like a celestial lighthouse mechanism, though at this moment it shines mostly in invisible rays. It also inherited a powerful magnetic field, billions of times stronger than Earth's own magnetic field, from its parent star, now intensified by the collapse. That magnetic field traps and guides particles in space, but unless those particle beams sweep past us, we would never know. They would remain a silent light, unseen and unfelt from afar. At the moment of its birth, the neutron star is searingly hot. The surface may be millions of degrees, far hotter than the surface of a normal star, like our Sun. Yet the neutron star's tiny size makes it appear only as a faint, bluish-white ember against the darkness. With no new fuel to burn, this heat will slowly radiate away into space. The neutron star will cool gradually over thousands and millions of years. For now, though, it remains a fiercely hot, compact sphere, an incandescent cinder left from the star's fiery life, shining softly with its residual heat. It is a remarkable scene. Where once a vast star thrived, now a tiny, dense core remains. This neutron star, only a few kilometers across, is the entire legacy of a supergiant. All the tumult and noise of the star's life have distilled into this silent, solid beacon. In the emptiness of space, it quietly persists, a testament to the strange and beautiful afterlives of stars. All around this tiny star, a new nebula is blossoming. The outer layers that were cast off in the supernova now form an expanding cloud of gas and dust. Immediately after the explosion, this cloud was brilliant, an intense flash of light and energy spreading outwards. But as moments turn to hours, and hours to days, the glare softens. What remains is an ever-growing veil of stellar debris, glowing faintly as it drifts into the surrounding darkness. It is the quiet afterglow of the once mighty star, a cosmic halo marking where the explosion took place. Filaments of glowing gas spread outwards in intricate patterns. Some regions shine in red hues from hydrogen gas, others in soft greens or blues from oxygen and other elements forged in the star. From a distance, the nebula would resemble a delicate, expanding shell, like a cosmic flower blooming and then slowly fading. It expands quietly, its material thinning out across trillions of kilometers. Every day, the nebula grows larger and more diffuse, its light dimming as the energy from the explosion dissipates into the emptiness. In the center of this expanding cloud, almost easy to overlook against the vastness, the neutron star remains. Compared to the brilliant nebula, the neutron star is just a tiny point of light, like a solitary ember at the heart of a fading fire. It glows with the heat of its formation, but its light is pale and subtle now, mostly visible in high-energy wavelengths that our eyes cannot see. If we were watching from a nearby vantage in space, we might barely perceive this faint, newborn star, nestled amid the debris of its progenitor. Over the next weeks and months, the supernova's visible glow fades away. What was once the light of 10 billion suns gradually diminishes, leaving only the faint luminosity of the expanding nebula and the central neutron star. As years pass, the nebula continues to expand and cool, growing larger and more diffuse. Centuries from now, it will stretch across many light-years of space, an ever-thinning veil of gas that eventually blends into the surrounding interstellar medium as a mere whisper of what once was. The neutron star, too, will dim slowly, cooling as it radiates away its heat. It will not go completely dark for a very long time, but its brilliant birth fire will calm to a steady, quiet glow. Drifting through space, the nebula carries in it all the elements the star forged during its life. There is carbon and oxygen that once fueled the star's core, calcium that was formed in the star's outer layers, and iron that accumulated in its final moments. These elements will mix with the surrounding interstellar gas. Perhaps, millions of years from now, some of this enriched material will coalesce into new stars, and maybe even new planets. After all, long ago this star itself may have been born from the cast-off remnants of an older star. In this way, the star's death is not truly an end, but a transformation. Its substance and essence will nourish new cosmic generations to come. Meanwhile, the neutron star persists, an almost eternal ember of its former self. It is utterly alone now, surrounded only by emptiness and the thinning traces of the nebula that it created. If the star had any planets orbiting it once, they are gone, either consumed in the explosion or flung into the void. All that remains in this region of space is the quiet neutron star and the ghostly cloud of its own remains. The cosmic stage that once held a brilliant giant is now left nearly empty, illuminated only by this one small, dense star, quietly shining in the darkness. Beyond the nebula's edge, the countless other stars of the galaxy continue to shine as if nothing has happened, their light distant and unchanging. The neutron star will spin silently in the darkness, gradually slowing over eons. Its strong magnetic field and rapid rotation might make it a pulsar, flashing beams of energy like a distant lighthouse. but only if those beams sweep across our line of sight. If not, it remains invisible to all but the most sensitive instruments. A silent pulsar, quietly holding the memory of the star that was. Here, in the quiet after the storm, this city-sized giant simply endures, a beacon of what remains after such cosmic upheaval. The chaos of the supernova has passed, and in its wake is profound calm. It is as if the universe itself has taken a deep breath. This calm invites reflection, a pause in the story of the star, but not the end. In this stillness, one chapter closes and another quietly begins, as the neutron star watches over the dispersing clouds of its former self, waiting in silence for whatever comes next. In the darkness of space, there was a time when even the most powerful telescopes saw nothing of the tiny remnants left behind by supernovae. These neutron stars, though immensely heavy and compact, drifted silently, invisible against the backdrop of the cosmos. For years they remained theoretical phantoms, quiet behemoths hidden in the void, their presence inferred only through calculations and imagination. Then one day, the silence was broken by a faint and mysterious rhythm. In 1967, at a radio observatory in Cambridge, a young astronomer named Jocelyn Bell noticed something strange on her long paper readouts. Amid the usual crackle and noise of the cosmic background, there appeared a series of equally spaced pulses. Each pulse arrived about 1 1/3 seconds after the last, repeating with uncanny precision. It was as if the universe itself had begun to beat a steady, gentle drum in time. At first, Jocelyn could hardly believe her eyes. She had spent long hours scanning those chart recordings by hand, eyes trained to catch any unusual scruff in the data. Natural celestial sources were expected to be chaotic or irregular. Yet here was a perfect cosmic metronome ticking away in the vast night. The signal was so regular, so deliberate, that she and her colleagues wondered if it might not be natural at all. Could this be interference from earthly sources? A stray signal from a radar or a passing satellite? Or could it be something far more extraordinary? Perhaps a beacon from another civilization? Half in earnest and half in jest, they nicknamed the source LGM-1 for Little Green Men 1, entertaining the whimsical notion that somewhere out in space, extraterrestrial beings might be sending out a greeting. Night after night, the mysterious pulses continued, steadfast and unchanging. Jocelyn checked and rechecked the equipment, ruling out every possible terrestrial cause. The pattern was coming from space, keeping time with the stars as the Earth rotated. And then, in the weeks that followed, another signal of the same kind was found in a different part of the sky. The chances of 2 separate alien beacons blinking in perfect rhythm were vanishingly small. With the discovery of a second pulsing source, the extraterrestrial hypothesis quietly faded. What remained was an even more profound realization. Nature was doing something we had never seen before. Astronomers soon concluded that these signals must be coming from an entirely new kind of cosmic object. They named them pulsars, short for pulsating radio stars. It was a poetic name for a remarkable phenomenon. A star that had died in a supernova cataclysm, yet now announced its undead existence through rhythmic radio beats. At last, one of the universe's quiet remnants had found a voice. With each pulse, a once silent neutron star was effectively standing up in the darkness and saying, "I am here." The scientific community was astonished. For decades, neutron stars had been predicted as the ultra-dense leftovers of supernova explosions, tiny cores left after a giant star's fiery death. Yet no direct evidence of them had been observed until that moment. Now, through these pulses, the existence of neutron stars was not just theory, but tangible reality. Here was proof that such exotic objects not only existed, but could spin and send signals across light years. The cosmos, once thought silent in its depths, was in fact alive with hidden heartbeats. Imagine the wonder of that discovery. A sphere only a few tens of kilometers across, the collapsed heart of a massive star, was spinning somewhere in the void and sweeping a beam of energy through space. Each time that beam swung past Earth, our radio antennas caught a fleeting whisper of it, a distant hello from a star we could not otherwise see. It was like spotting the blink of a lighthouse on a dark sea, invisible most of the time, but undeniable when its light aligned with our gaze. Each pulse that reached us had been travelling for ages, traversing the emptiness of space before arriving at our world to tell the story of its source. As the nature of pulsars became clear, awe settled in. Only an object as extraordinary as a neutron star could produce such precise cosmic ticking without tearing itself apart. The first pulsar's steady beat implied a rotation so stable and rapid that it defied ordinary experience. It turned out that little green men were not needed to explain the signal. Mother Nature was inventive enough. A neutron star, spinning like a cosmic dancer with a brilliant spotlight, was the culprit. This revelation was as exciting as any alien signal, for it opened up a new realm of astrophysics and deepened our understanding of stellar evolution. That first mysterious celestial pulse was no longer a mystery. It was the heartbeat of a dead star, made audible across the cosmos. In that moment, a bridge was formed between theoretical physics and observation. The long silent neutron stars of prediction were now speaking in the language of pulses and periods. Astronomers around the world tuned in with eager ears and realized they had found natural clocks in the sky. The universe had been quietly keeping time with these spinning stars, and at last we had noticed. The discovery of pulsars ranks among the great serendipitous moments in science. A careful observer, a strange signal, and an open mind led to the unveiling of something wondrous. Soon, radio telescopes everywhere began searching for more of these cosmic lighthouses. And indeed, more came to light one by one. Each new pulsar found confirmed that our galaxy was sprinkled with these tiny spinning beacons. What had once been an isolated curiosity turned out to be a common, if extraordinary, feature of the universe. Today, thanks to that first detection, we know of thousands of pulsars scattered throughout the Milky Way. Each pulses at its own characteristic rate, some faster, some slower, but all are united by the same basic mechanism. They are quiet, stellar remnants turned cosmic metronomes. The initial mystery has given way to a rich field of study, yet the sense of wonder endures. Even now, when one listens to a pulsar's signal, often converting it to audible clicks or beeps, one cannot help but feel a quiet thrill. It is the sound of a star's afterlife, a steady, unyielding rhythm marking the passage of celestial time. Jocelyn's discovery was not immediately shouted from the rooftops. She and her team carefully checked and rechecked, holding off announcement until they were certain the signal was neither a fluke nor man-made interference. By early 1968, the evidence was overwhelming, and the finding was made public, sending ripples of excitement through the scientific community. Here was something genuinely new under the sun, or rather, beyond it. A cosmic heartbeat where none had been expected. Astronomers around the world eagerly turned their radio ears to the sky, and it wasn't long before they found other pulsars flashing their hello. One by one, these lighthouses in the void began to reveal themselves in observatory data, each with its own tempo. The initial enigma blossomed into an entire population of objects, each one waiting to tell its story through a unique rhythm. The term pulsar quickly entered the scientific lexicon. Short, catchy, and evocative, it captured the essence of what was observed: pulsating stars. Behind that name lay profound implications. In detecting pulsars, astronomers had essentially stumbled upon rotating neutron stars, entities that until then had been purely theoretical. The confirmation was a triumph for physics and astronomy, cementing our understanding that nature could create ultra-dense objects with astonishing properties. In 1974, the Nobel Prize in Physics was awarded for the discovery of pulsars, though controversially, Jocelyn Bell was not a recipient, as she was a graduate student at the time of discovery. Jocelyn herself took this in stride, often quipping that the pulsars were her prize. The real reward was the thrill of uncovering something so marvelous. The world now knew that neutron stars were real, and that they could be observed and studied through their pulses. A new window on the universe had swung open. And what gifts they turned out to be. In the blink of an eye, the cosmos had presented us with natural clocks scattered across the galaxy. For humanity, which had long marked time by the rhythms of our own planet's rotation and orbit, this was a revelation. Out in the depths of space, dead stars were ticking away the moments with incredible precision, utterly oblivious to us, yet extraordinarily useful to our understanding. The discovery of pulsars transformed radio astronomy from a niche pursuit into a powerhouse of discovery. These objects became tools for probing fundamental physics, testing theories of gravity, and measuring distances across the galaxy. Yet they were also, simply, sources of wonder. Each pulse was a cosmic heartbeat we could detect, a reminder that the universe has its own hidden cadence. Looking up at the night sky now carried a new excitement. Invisible to our eyes, scattered among the stars, were those tiny blinking beacons, pulsars quietly ticking away. They reminded us that the universe still held surprises, that even after a star's violent death, something steady and beautiful could emerge. One particularly poignant example was the pulsar found in the Crab Nebula. In July of 1054 AD, skywatchers in China and elsewhere recorded a guest star suddenly visible in daylight, a supernova explosion in what we now know is the Crab Nebula. Fast forward nearly 1,000 years, and in 1968, astronomers discovered a pulsar at the heart of that nebula, flashing about 30 times each second. There, in that whirling beacon, was the tiny collapsed core of the star that had exploded so long ago, still beating, centuries after the supernova's light first reached Earth. Ancient observers saw the brilliant death of a star. Modern ones now witness its rotating corpse. Such connections beautifully close the loop between history and science, showing us directly how a supernova's fury can give birth to a neutron star's pulse. Having explored how neutron stars form in stellar explosions, we now appreciate what came next. The once silent remnants began speaking through their pulses. Through those regular flashes, these stellar corpses have become cosmic metronomes. Their discovery was just the beginning of an ongoing story, one that continues to unfold as we learn to listen more closely to the messages they send across the cosmos. Far out in the cosmic ocean, the newly discovered pulsars revealed themselves as celestial lighthouses. But what exactly were these beams of energy, sweeping through the void with clockwork precision? To understand that, imagine a lone lighthouse on a distant shore. Its lamp rotates, casting a narrow beam of light around the horizon. An observer far away in the dark sees the lighthouse not as a constant glow, but as a periodic flash each time the beam points their way. This is precisely how a pulsar works, only on a vastly grander scale, and with a beam not of visible light, but of invisible radio waves, and sometimes high-energy X-rays or gamma rays. The neutron star's rapid rotation, combined with its intense magnetic field, creates twin searchlight beams that cut across space. Each time one of those beams sweeps past Earth, we detect a pulse. The mechanism behind this cosmic lighthouse is both elegant and extreme. A neutron star is a tiny sphere, perhaps only 20 kilometers in diameter, yet it contains more mass than our Sun. When such a massive star's core collapsed to form the neutron star, it also inherited the star's rotation. Like an ice skater pulling in her arms and spinning faster, the shrinking core twirled into a rapid spin. What might have been a leisurely rotation in the original giant star becomes, after collapse, a furious whirl. Many pulsars rotate dozens of times each second. Some especially fast ones, appropriately called millisecond pulsars, spin hundreds of times per second, a mind-boggling speed. Imagine an object the size of a city, containing the mass of a sun, spinning so fast that a point on its equator moves at a significant fraction of the speed of light. It defies common sense, yet nature presents us with these astonishing rotators. Crucial to a pulsar's nature is its magnetic field. Neutron stars are endowed with immensely powerful magnetic fields, trillions of times stronger than Earth's own field. During the core's collapse, the star's magnetic field intensified, concentrating like lines on a crumpled piece of paper. The result is a magnetic engine of incredible might. As the neutron star spins, its magnetic field whips around, accelerating charged particles, such as electrons, to tremendous energies. These particles, trapped by the magnetic field, stream out along the star's magnetic poles. In doing so, they emit radiation. Radio waves primarily, but often X-rays and gamma rays as well, focused into tight beams. Thus, the neutron star becomes a cosmic beacon, with energy gushing out along its magnetic poles. Though no person could ever safely approach a neutron star, we can still imagine what it might be like up close. Against the darkness of space, a pulsar would appear as a tiny, fiercely heavy sphere. Its surface might be dim to human eyes, yet around its magnetic poles, there could be a faint bluish or reddish glow, where exotic processes accelerate particles to high energies. If you were somehow hovering nearby, ignoring the lethal gravity and radiation for this thought experiment, you might see twin jets of particles and light pouring out from the star's opposite poles. They would sweep around as the star spins, like the revolving beams of a lighthouse. If one of those beams passed over you, you'd be bathed in intense radiation for a brief instant each rotation. The neutron star itself, only kilometers across, might look unremarkable at first glance, perhaps a dark, charcoal grey orb, but its rapid spin and incredible mass would visibly distort the space around it. Gravity would curve the path of light near the star, so you could actually glimpse parts of the far side of the pulsar bent into view. It would be an eerie, mind-bending sight, as if the star were enclosed in a funhouse mirror of its own making. It's a scene no human will likely witness directly, yet through our instruments and the laws of physics we can picture this bizarre world. A collapsed star, tiny yet powerful, spinning in the void with searchlight beams eternally on. Such an image reinforces just how extraordinary pulsars are, truly unlike anything we experience in daily life. However, there's a twist. The magnetic poles are not necessarily aligned with the star's axis of rotation, just as Earth's magnetic north pole is offset from its geographic north pole. Because of this misalignment, as the neutron star spins, the magnetic poles and their beams sweep around in circles. Think of a wobbling top with a flashlight attached. The light would trace a circle as the top spins. For a distant observer, situated in the path of that sweep, the flashlight's beam would appear as flashes at regular intervals. Likewise, when the path of a pulsar's beam intersects our line of sight, we perceive pulses of emission at each rotation. Not every neutron star will appear as a pulsar to us. If a star's beams never cross Earth, we would never know it's there through radio pulses. In those cases, the neutron star remains effectively invisible, a quiet wanderer in space, with only its gravity betraying it. Astronomers suspect that for every pulsar we detect, there may be many more neutron stars spinning silently, their beams aimed elsewhere, sweeping the darkness without an audience. It's humbling to realize our telescopes might be catching just a small sample of a much larger cosmic orchestra. The universe keeps many of its quiet behemoths to itself, and orientation is the key to whether a neutron star shares its heartbeat with us or stays in the dark. The pulses themselves carry a wealth of information. The interval between pulses tells us the rotation period of the neutron star, essentially the length of its day. These periods can range widely. Some pulsars spin slowly, taking a few seconds for one rotation, resulting in a languid blink, blink, blink that might remind one of a steady drip of water echoing in a cave. Other pulsars spin much faster, perhaps 10 times a second, or 30 times, or hundreds of times. These create a rapid beat, so quick that if converted to sound, it would resemble a hum or musical tone rather than distinct ticks. The fastest pulsars, spinning about 716 times each second, in fact that is the record so far, complete a full turn in the literal blink of an eye, far faster than a hummingbird's wing. To our senses, such a pulsar's flashes would blur into a continuous buzz if we could somehow watch it directly. But radio telescopes pass each individual burst with precision. It's incredible to consider the stability of these cosmic clocks. A pulsar's rotation is so consistent that its pulses can arrive as predictably as the ticks of a well-made metronome. The timing can be so regular that some pulsars rival atomic clocks in their steadiness over months and years. One could, in theory, set a clock by a pulsar's beat, at least for a while. Over very long timescales, however, even pulsars gradually change. As they emit radiation and winds of particles, they lose energy and slowly spin down. A pulsar that flashes, say, 30 times a second today, will flash a little slower millennia from now. But the change is usually imperceptibly small on human timescales, fractions of a second over many years. To detect such slowing, scientists carefully measure pulse arrival times over decades. It's as if the cosmic lighthouse's rotation is powered by a giant, wound-up spring that is ever so gently unwinding. Eon by eon, the lighthouse beam turns more lazily as the star's energy dissipates. Yet, even in its steadiness, a pulsar is not absolutely unchanging. Over very long times, the pulse rate does decline, like a heartbeat gradually slowing as a creature ages, albeit on a scale of millions of years. A young pulsar might have a heartbeat of dozens of beats per second. After eons, that same pulsar could slow to only a few beats per second or less. The energy that powers its rotation is being drained away, carried off by its radiation and particle winds. The neutron star's spin is essentially its lifeblood, and as that spin ebbs, the pulses become farther apart. However, this decline is so gradual that to our measurements, the pulsar's rhythm still seems almost eternal. Generation after generation, the star keeps time, slowing only imperceptibly. Sometimes, though, the heartbeat of a dead star can surprise us. Astronomers have observed that some pulsars experience sudden, tiny jumps in their rotation rate, events we call glitches. One moment, the pulsar is beating steadily. The next, it's ever so slightly faster than before. Imagine listening to a perfectly timed clock that suddenly ticks a hair too quickly for just one beat before returning to its regular rhythm. In pulsars, such an occurrence is like a heart skipping a beat. In the stellar heart, it might happen when the superfluid interior of the neutron star transfers a bit of its angular momentum to the crust, spinning the crust up a notch. It could also be triggered by a starquake, a crack or shift in the star's solid crust as it adjusts to the stresses of spinning down and cooling. The crust is immensely strong, far stronger than steel, but even it can occasionally fracture under the strain. When that happens, the star's rotation jumps minutely. To an astronomer measuring the pulses, it's a startling anomaly, a brief hiccup in an otherwise steady rhythm, an instant where the cosmic heartbeat betrays a deep internal adjustment. These glitches are precious clues. They tell us that a neutron star's interior is not a uniform, rigid ball, but a complex layered system capable of sudden rearrangements. It's as if we were watching a far-off lighthouse and noticed a tiny jitter in its light, an indication that something inside the lighthouse machinery shifted. With pulsars, that machinery is nuclear matter at supradense states we cannot replicate on Earth. Each irregularity in the otherwise regular beat is like a telegram from the star's core, providing evidence of superfluid neutrons sloshing or crustal plates shifting. In the calm and reliable rhythm of a pulsar, these rare hiccups speak volumes about the wild conditions hidden beneath its surface. Interestingly, not all neutron stars reveal themselves as neatly as pulsars do. A rare few, called magnetars, behave quite differently. Magnetars have magnetic fields even stronger than a typical pulsar's, hundreds of times stronger in fact, and their rotations are often slower. They might not produce regular radio pulses at all. Instead, a magnetar occasionally unleashes sudden, intense bursts of high-energy radiation, X-rays and gamma rays, that can momentarily dominate the sky. One might think of these as a different kind of heartbeat, not the steady ticking of a healthy heart, but sporadic, powerful surges. When a magnetar flares, for a brief moment it can outshine every other X-ray source in the galaxy, then it fades back into quiescence. These magnetar outbursts are thought to be caused by stresses in the star's ultra-strong magnetic field snapping the crust, a dramatic cousin to the subtle glitches of ordinary pulsars. They remind us that even among neutron stars there is great diversity. Some choose a calm, steady rhythm, while others live in relative silence, punctuated by rare moments of fury. In their quieter periods, magnetars join the ranks of silent neutron stars that escape our notice, objects that only announce themselves through an occasional cosmic roar rather than a steady beat. Magnetars are an extreme case, and we will encounter them again later in our journey. For now, they serve as a reminder that the neutron star family includes both the gently ticking and the violently eruptive. For the most part, however, a pulsar's heart beats on steadily. It is this steadfast regularity that makes pulsars such powerful tools for science. But it also gives them a kind of personality in the eyes of those who study them. Some astronomers affectionately compare listening to a pulsar's signals to hearing a star's heartbeat. When converted to audible sound, the pulses do resemble a rhythmic series of ticks or beeps. There is something poignant about those sounds, knowing they originate from a collapsed star spinning in the cosmic darkness. It is the sound of a star's remaining life, a metronome of a dead sun echoing across space. Yet one must remember that even these heartbeats will eventually fade. As stable as pulsars are, they are not eternal perpetual motion machines. Given enough time, a pulsar's energy does wane, its rotations slow to a crawl, and the once bright beams can weaken and cease. In terms of our metaphor, the heart will one day stop. What remains then is a truly silent neutron star, a cold, inert remnant with no pulses left to give. Perhaps it will still spin quietly in the dark, but without a strong magnetic beacon, it will blend into the cosmic background, virtually undetectable. The transition from a pulsar to a silent neutron star is like the final death of the star, the end of its second life as a lighthouse. It's fascinating and a bit melancholic. A pulsar's heartbeat can last millions, even tens of millions of years, but not forever. The universe slowly quiets its once noisy children. Pulsars that were born flashing furiously eventually age into obscurity. We happen to live in an era when many pulsars are still ticking, and we have the technology to catch their signals. In the far future, the galaxy might be a quieter place as the last pulsar hearts wind down. But for now, each pulsar we observe is a reminder of dynamic processes still unfolding long after a star's dramatic death. In some cases, a pulsar's heartbeat might be altered or revived by external influences. If a dead neutron star, one that's gone quiet, were to encounter fresh fuel, perhaps by pulling gas from a companion star, it could spin up again and potentially relight its beam. The cosmos provides these second chances, a kind of cosmic defibrillation that can restart a faltering stellar heart. Indeed, the millisecond pulsars we discussed are examples of old, slow neutron stars rejuvenated to incredible spin rates by accreting matter from a neighbor. In their old age, they found a way to beat faster than ever, a revitalized heart racing along after a long period of rest. Every pulsar tells a story through its heartbeat. Some beat steadily from birth and slowly fade with age. Others might skip or stumble on occasion, with glitches, then continue on as before. Some are born to brief glory, spinning madly and emitting fierce beams, only to exhaust their energy relatively quickly. Others manage to keep going for the long haul, their heartbeats echoing through the galaxy long after the events that created them. And there are those that remain hidden from us entirely. Neutron stars, whose alignment or low activity make them practically invisible. These are the silent pulsars, the quiet hearts we cannot easily detect. They remind us that absence of a signal is not evidence of absence. The quiet ones are still out there, ticking softly without our awareness. The notion of a silent pulsar might sound like a paradox. A pulsar that doesn't pulse, at least not in any way we can observe. But it's an important concept, representing both the final, ghostly stage of a pulsar's life and the limitations of our own observation methods. Somewhere in our galaxy, there may be an ancient neutron star whose magnetic field has weakened and whose rotation has slowed to a whisper of its former self. To our radio telescopes, it's effectively mute. Its once strong heartbeat is now too faint to register, or perhaps its beam no longer intersects Earth at all. In either case, it is a neutron star, just the same, quietly holding on to its mass and mystery, awaiting some future event or improved technology to reveal it. Understanding the heartbeats of dead stars, their rise, their steadiness, and their eventual silence, gives us a profound perspective on time and change in the universe. These objects bridge the gap between violent death and quiet afterlife. They show us that even in the wake of cosmic destruction, there can be order and beauty, like a phoenix that doesn't blaze anew, but instead persists as a steady pulse in the darkness. Each pulsar's heartbeat is a tiny beacon of continuity amid the chaos, a reassurance that the story of a star doesn't end with its explosion. There is a calm epilogue, written in pulses, that can last far longer than the brief ferocity of a supernova. As we listen to the heartbeats of these dead stars, we find ourselves connected to events and environments utterly beyond everyday experience. The slow tick of a pulsar invites us to contemplate matter, squeezed to unimaginable density, and space-time curved by intense gravity. Yet it also offers a strange comfort, a sense of reliable rhythm in a universe that often seems turbulent and unpredictable. Many who work with pulsars describe a kind of reverence in the act, a feeling not unlike listening to the rhythmic crashing of distant waves on a shore, though here the waves are pulses of radio waves arriving across light years. It reminds us that even in the apparent silence of space, there is music. The cosmos has its quiet beats, its hidden harmonies. In the end, a pulsar's heartbeat is both a physical signal and a symbol. It's a real, measurable phenomenon, the rotation of a dense core, sweeping out beams we can detect. But it's also a symbol of resilience and cosmic rhythm. The idea that after catastrophic endings can come a gentle, steady coda. It's the universe's way of telling us that even the husk of a star, a city-sized ball of neutrons, can have a sort of second life, a heartbeat that speaks across the void. Our exploration of neutron stars and pulsars has so far taken us from the tumultuous birth of these objects to the steady signals they emit across the void. We have learned to detect those signals and use them to illuminate aspects of the cosmos that would otherwise remain dark and unknowable. But there are more chapters to this story. Not all neutron stars manifest as friendly beacons. Some hide behind veils of magnetism or linger in apparent silence, detectable only through their gravity or through rare, dramatic outbursts. Even pulsars, with all their regularity, can surprise us with exotic behaviors that challenge our understanding. As our journey continues, we will delve into the quieter side of these cosmic behemoths, the truly silent pulsars and other enigmatic expressions of neutron star nature that await us, deepening the mystery and majesty of these quiet behemoths. Across the Earth, radio telescopes quietly listen to the sky, attuned to the faint beats of pulsars. In remote observatory sites, perhaps a giant dish nestled in a valley, or an array of antennae spread across a desert plain, astronomers sit in dim control rooms, watching data scroll by on glowing screens. They are, in a very real sense, the timekeepers of the galaxy, gathering the ticks of celestial clocks and deciphering what those rhythms mean. Each pulse that arrives from a far-off neutron star is logged with a timestamp. Each gap between pulses is measured with care. Through these diligent observations, scientists have learned how to use pulsars as precise tools, turning the cosmos into their laboratory. On a clear night at one such observatory, the scene is almost otherworldly. The vast bowl of a radio telescope tilts upward, shimmering faintly under starlight, as it pivots to follow an invisible target. Inside the control room, red lights cast a faint glow and a hush prevails. A faint crackle from the speakers soon gives way to a rhythmic series of ticks. Those sounds are the pulses of a distant pulsar, converted into audible clicks. The astronomer on duty listens with headphones, closing her eyes for a moment. Each tick comes separated by a precise interval, a cosmic heartbeat, steady and unfaltering. It might be 1 click every second, or 30 rapid clicks each second, depending on the pulsar being observed. The effect is hypnotic. In that quiet moment, with the night breeze gently brushing the telescope's receivers outside, and the vast silence of the stars pressing in, she feels an intimate connection to a stellar remnant light years away. Here, in the stillness, the heartbeat of a neutron star becomes something almost personal, a steady, patient signal echoing across time and space into human ears. When a pulsar's signal is transformed into sound like this, one can practically hear the cosmos at work. Some pulsars tick methodically, perhaps a slow click, 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 like a calm metronome counting off seconds. Others, especially millisecond pulsars, produce such a rapid stream of ticks that they blur into a single continuous tone, a gentle whir that rises and falls softly. To listen to these sounds is to gain a visceral sense of the pulsar's character. A slow pulsar sounds like a relaxed, deliberate heartbeat, whereas a fast one hums like a high-pitched electronic note. It is eerie and enchanting in equal measure, the ghostly music of objects too far to see, yet captured through their rhythm. For decades now, astronomers have been listening to pulsars in this way, not just to appreciate their cosmic music, but to use them as precise instruments for understanding the universe. The extreme regularity of many pulsar pulses allows scientists to treat them as cosmic clocks. By comparing the arrival times of pulses to the beat of Earth's best atomic clocks, any slight discrepancy stands out. These discrepancies are gold mines of information, revealing phenomena that might otherwise remain hidden. In essence, each pulsar we monitor is like a celestial observatory in its own right, placed wherever that pulsar resides, taking the galactic pulse of its surroundings and sending the data to us via its ticks. One of the most astonishing uses of pulsar timing was the discovery of planets outside our solar system. In the early 1990s, astronomers studying a particular pulsar noticed tiny irregularities in its otherwise clockwork timing. The pulses were arriving a bit early at some times, and a bit late at others, in a pattern that repeated. After careful analysis, they realized that the pulsar wasn't alone. It was being tugged back and forth by the gravity of at least 3 orbiting planets. The neutron star's steady beat acted like a drum being slightly accelerated or decelerated as it danced with unseen companions. By measuring those subtle shifts, the astronomers could infer the masses and orbits of the planets making the pulsar wobble. Thus, the first confirmed exoplanets were not found around a sun-like star, as many might have expected, but around a pulsar, a dead star's faint heartbeat revealing the presence of worlds. It was a revelation. Even in the aftermath of a supernova, a kind of planetary system could exist, and we only detected it by listening to the star's rhythmic signals. It was a surprise to many that a neutron star, an object so hostile with radiation and intense gravity, could have planets at all. One can only imagine what those worlds might be like, bathed in periodic blasts of energetic particles and radiation from their pulsating sun. But their discovery underscored the sensitivity of pulsar timing. The fact that we could sense the gentle gravitational pull of small planets on a neutron star from thousands of light years away speaks volumes about the precision of our measurements. The pulsar's beats, so steady and so faithfully recorded, allowed astronomers to deduce the existence of bodies far too dim to see directly. In a sense, the pulsar itself acted as the detective, its timing the clue that gave the game away. To this day, pulsar PSR B257 plus 12, the one with those planets, remains an object of fascination, a stellar system turned upside down, a sun that died, and planets that somehow persisted. Pulsars have also become key probes for testing the nature of gravity itself. In the 1970s, a particularly important discovery was made. A pulsar in a binary system. Two neutron stars orbiting one another. This system, discovered by Russell Hulse and Joseph Taylor, provided an unprecedented natural laboratory for Einstein's theory of general relativity. As these two dense stars orbited each other, they stirred the fabric of spacetime and slowly spiraled inward. According to Einstein's theory, such a binary should radiate energy in the form of gravitational waves, subtle ripples in spacetime, causing the orbit to shrink. By meticulously timing the pulsar's ticks and tracking how its orbital motions changed over years, Hulse and Taylor were able to show that the orbit was indeed tightening over time. The rate of change matched almost perfectly what relativity predicted if gravitational waves were carrying off energy. This was the first indirect evidence of gravitational waves, decades before we could detect those waves directly with instruments on Earth. Once again, a pulsar's steady beat had proved to be a powerful tool of discovery. By acting like an extremely precise clock, one moving in a strong gravitational field, the pulsar allowed physicists to test gravitational theory in conditions far beyond any laboratory experiment. The success was profound. It validated Einstein's predictions on cosmic scales and earned Hulse and Taylor the 1993 Nobel Prize in Physics. They often acknowledged that the true hero of the experiment was the pulsar itself, a tiny, distant ticking clock that enabled humans to confirm fundamental physics. In listening to that double star dance, we confirmed that gravitational waves were real, and that even in its death, a star could help illuminate the workings of the universe. Today, we have even grander ambitions for pulsar timing. Around the globe, collaborations of scientists are monitoring dozens of millisecond pulsars, those ultra-fast, ultra-precise timekeepers. By comparing their signals over long periods, these teams hope to detect gravitational waves of a different kind. Not the fleeting chirps from merging black holes that facilities like LIGO have detected, but a constant, low-frequency humming caused by gigantic black holes in the cores of distant galaxies merging over eons. The idea is bold and beautiful. Use the galaxy itself, with pulsars as metronomes, to sense the stretching and squeezing of space-time as colossal masses collide across the universe. Here's how it works. As a gravitational wave passes through our region of space, it would very slightly alter the distance between Earth and each pulsar, effectively changing the arrival times of the pulses by a tiny amount. For an individual pulsar, this effect would be almost impossible to discern. But if many pulsars across the sky all show a coordinated drift in their ticking, that could be the fingerprint of a gravitational wave gently rocking our part of the Milky Way. Each pulsar in the timing network is like a buoy floating on the cosmic ocean. When a big wave, in space-time, rolls by, the arrival of pulses from some buoys might come a bit late, from others a bit early, in just the pattern a gravitational wave would produce. This effort, known as a pulsar timing array, is currently underway. It requires extraordinary patience and precision, the kind where even a difference of a few 10 billionths of a second is meaningful. Years, even decades, of data are combed for the faint fingerprint of gravitational waves. If and when the signal is detected, it will open a new window on the universe, allowing us to hear the slow symphony of merging galaxies and other colossal events through the steady beating of pulsars. In a sense, we are using neutron stars scattered across the galaxy as a single, gigantic detector, an observatory that spans light years. It's a testament to human ingenuity and nature's provision of these wonderful clocks that such an audacious experiment is even conceivable. Beyond their role in cutting-edge research, pulsars have practical potential for future exploration. One day, if spacecraft carrying humans or robots venture far beyond the solar system, they will lose the familiar navigational aids we use near Earth, like GPS satellites or even sight of the sun. Pulsars could fill that role as cosmic signposts. Each known pulsar has a unique rotation period, a sort of signature tick, and their positions in the sky are very well charted. A spacecraft equipped with an X-ray or radio detector could measure the arrival times of pulses from a few pulsars and compare them to an onboard clock. By seeing how ahead or behind schedule those pulses are, the craft could triangulate its own position in space, much like how GPS uses timing signals from multiple satellites. This isn't just a theoretical idea, it has been demonstrated in principle. In 2017, an experiment on the International Space Station used signals from pulsars to pinpoint the station's orbit. It was a proof of concept for a galactic positioning system. The concept worked. Using pulsars as beacons, the onboard system could determine the station's location within a few kilometers. Not as pinpoint as GPS, but certainly good enough to navigate through space. In the future, an interstellar probe might roam between the stars and periodically tune into the cosmos to get its bearings, listening for the telltale pulsations of a few reliable pulsars. The lighthouses in the void would literally guide our journey, just as mariners of old used the stars. It's poetic to think that the dead hearts of stars could one day help living travelers find their way through the dark seas of space. Even in the present day, pulsars have been incorporated into humanity's attempts to communicate our presence to the wider universe. When the Voyager 1 and 2 probes were launched in the late 1970s to head into interstellar space, each carried a golden record, a sort of time capsule of earthly sounds and images for any future finders. Affixed to each record's cover was a diagram, a kind of cosmic map showing our sun's location relative to 14 pulsars scattered around the galaxy. Each pulsar was represented by a line radiating out from the sun, and alongside each line was etched the pulsar's rotation period in binary notation. The idea was that any intelligent beings who eventually encounter Voyager might recognize those pulsar periods. Since each pulsar's period is distinctive and also very gradually changing, they could use that information like a galactic fingerprint to identify which pulsars we meant and thus triangulate where our solar system lies. In essence, we used the pulsar network as an address label for Earth. We trusted these steady beacons, these lighthouses in the void, to act as reference points that span both space and time, perhaps guiding someone to our door long after we're gone. How remarkable that an object once nicknamed for little green men was later employed as a beacon for potential little green men out in the cosmos. Through all these endeavors, from probing extreme physics to mapping the galaxy, the act of listening to pulsars has connected us intimately with phenomena far beyond our ordinary experience. Each observing session, each detection of a pulse arriving exactly on time, or not exactly on time, is like a brief handshake with a distant star. We've learned that by attending carefully to these celestial heartbeats, we can eavesdrop on all sorts of cosmic secrets. It is as if we have tuned into a hidden radio channel where the universe broadcasts messages about what it's doing on scales grand and small. A pulsar might tell us about an asteroid that drifted too close and disrupted its timing, or whisper of the diffuse plasma it traverses by arriving a tad late at certain frequencies. In listening, we become participants in a cosmic conversation. The neutron star sends its greeting in the form of pulses, and we respond with understanding, decoding the information and incorporating it into our knowledge. Moreover, pulsars have given us a new sense of scale and stability. Here on Earth, we've built precise clocks out of vibrating atoms to mark the seconds. But nature offers clocks on an entirely different scale, the whirling of neutron stars, which can be as regular as any man-made timepiece. It's humbling and astonishing to think that a 20-kilometer sphere of neutrons spinning hundreds of times a second can keep time better, in some cases, than the finest Swiss watch or atomic clock. These stellar clocks operate under conditions wildly different from any lab on Earth, yet they tick along so predictably that they enable some of the most precise measurements ever made. Pulsars remind us that the universe has its own timetable. They beat out milliseconds and megayears with equal ease, linking human researchers to events that unfold on geological or even cosmic timescales. We have begun to use these cosmic metronomes to anchor our reference frames, to test the stability of nature's constants, and maybe one day to navigate spacecraft. In doing so, we are synchronizing our human perspective with the timing of the stars. As we continue to observe and interpret these pulses, our understanding of the universe deepens. Each new pulsar discovered can refine our models of the galaxy's structure. For instance, by using pulsar signals to map out the distribution of interstellar gas, since the radio pulses get slightly delayed by the interstellar medium, revealing its density. Each carefully timed pulsar can improve our search for subtle gravitational effects permeating space. We've found pulsars in all sorts of environments now. Solitary pulsars spinning in splendid isolation. Pulsars paired with other neutron stars, locked in gravitational dances. Pulsars closely orbiting black holes, a scenario anticipated to test physics in extremely curved spacetime. And pulsars with planets, that most uncanny of configurations. Each arrangement offers its own insights. A double pulsar system allows a high-precision ballet of clocks to test general relativity. A pulsar around a black hole could one day push the limits of our theories of gravity. Pulsars with planets show that planetary systems can arise or survive, even from stellar ashes, hinting at resilience and second chances in the cosmos. The variety of circumstances in which pulsars are found keeps astronomers both busy and excited. It seems that whenever we think we've heard all the notes pulsars have to play, a new discovery introduces another variation on the theme. In recent years, for example, we've identified pulsars that occasionally turn off their pulses for some periods, so-called intermittent pulsars, and others that switch their emission mode as if toggling between different states. These behaviors continue to challenge our understanding and deepen the intrigue of pulsar science. Listening to the celestial metronome is not just a technical endeavor, it's also a deeply human and poetic one. There is something quietly profound about tuning into a rhythm that originates from a collapsed star thousands of light years away. In those moments of listening, perhaps alone at night in a control room, headphones on as the data pours in, an astronomer might feel the boundary between ourselves and the cosmos blur just a little. The steady beat of the pulsar can induce a sense of calm and contemplation. It's a reminder that beyond the hustle of earthly life, there are islands of stability in the universe, ticking away relentlessly. Many who have experienced this speak of a sense of connection and perspective. Problems of the day shrink in significance compared to the thought of a star's core, heavier than the entire Himalayas, yet only the size of a city, spinning in perfect rhythm long after its fiery death. It's almost a meditative experience. Just as one might feel soothed by the rhythmic crashing of ocean waves or the patter of rain, there is solace in the idea of these distant heartbeats, so regular and reliable, echoing through the cosmos. The pulsar doesn't know or care that we are listening, but in listening, we give the pulsar's existence meaning relative to us. We make it part of our story, and it makes us part of its story. Our journey through neutron stars and pulsars in this part of the documentary has taken us from the initial mysterious signal, that first gentle cosmic pulse, to the sophisticated ways we now use pulsars to explore fundamental physics and envision future navigation among the stars. We have seen how a chance discovery grew into a rich dialogue between humanity and the cosmos. We've also seen hints that not all is straightforward. There are silent actors on this stage, neutron stars that don't broadcast their presence so obviously. As we move forward, we'll turn our gaze to those quieter characters and to the dramatic episodes that pulsars and their kin can undergo. The lighthouse beacons have guided us this far, but beyond the beam's reach lies the deep night where other secrets lurk, the domain of the truly silent pulsars and other exotic phenomena. That is where our adventure will take us next, as we continue to explore these quiet behemoths and the silent depths of the cosmic ocean. Time flows onward, and even the steadfast heartbeat of a pulsar cannot keep its pace forever. Across the ages, a pulsar's once frenetic rhythm begins to ease and slow. In the cosmic night, where it once flashed brightly many times each second, it now rotates more languidly, a celestial metronome winding down. With each rotation, the neutron star sheds a bit of its energy to space, like a spinning top gradually losing speed. The proud beacon that signaled across light years now fades, its pulses growing fainter and farther apart in time. One could imagine the scene in fast forward. A vibrant young pulsar spinning furiously in the aftermath of its birth, then gradually, almost imperceptibly, decelerating. Decade by decade, century by century, its beam sweeps more slowly. If we could watch from a distance, the rapid strobing might become a gentle blinking over millennia. What was a torrent of flashes becomes a steady, slowing rhythm, a heartbeat weakening as the years roll on. The change is too slow for a single human lifetime to notice, but across cosmic time, the pulsar's lively dance does quieten. As eons pass, the pulsar's slowdown becomes profound. What was once a brisk spin decelerates to a crawl. Every pulse grows weaker, the interval between them stretching longer. Eventually, a moment comes when the emission falters entirely. The star's magnetic engine can no longer power the lighthouse beam. It has crossed a mysterious threshold astronomers call the pulsar death line. Beyond this point, the star falls silent and its radio heartbeat ceases. After tens of millions of years of steadfast ticking, the cosmic clock simply stops. In that silence, the pulsar effectively dies to our eyes. It may not be a sudden dramatic explosion, but a quiet transition. One moment there are faint pulses arriving across the light years. The next moment, nothing. The neutron star is still there, spinning in the darkness, but it no longer sends its familiar signals. There is a hush where once there was a cosmic song. The final pulse may have been indistinguishable from many before, yet after it, the beacon never rises again. It's as if a final breath has been exhaled, and the star has slipped into a deep slumber, invisible to anyone listening for its call. Yet death here is not destruction. The neutron star remains, but its dynamic spirit is gone. All that energy that once blazed from its magnetic poles is spent. The object that lingers is a hushed remnant, a dense, dark sphere drifting through space with hardly any sign of life. Astronomers sometimes speak of a pulsar graveyard, a poetic name for the fate of pulsars that have gone quiet. One by one, aging pulsars join this silent cemetery of stars. Spinning still, but slowly, these extinct pulsars are like ghostly lanterns with no light, neutron stars that have lost their pulse. If one were to encounter such a star up close, it would appear unremarkable to the eye. Perhaps a black silhouette against the starry background, offering no clue of the fireworks it once produced. The neutron star still carries incredible mass and density, but now it drifts quietly. Its magnetic field, while still strong, no longer whips particles into bright beams. It is a stellar core left in limbo, matter that has survived a supernova, condensed into an object only a dozen kilometers across, and now simply existing. The drama and noise of its youth are memories now, recorded only in the effects it left on its surroundings. In the void of space, it is as silent as a tombstone, marking the spot where a pulsar once shone. The lifetime of a pulsar's light is surprisingly brief on cosmic scales. 10 million years, the blink of an eye compared to the billions of years a normal star can shine. And the pulsar's shining phase is over. In fact, you could fit 1,000 pulsar lifetimes into the lifespan of an ordinary sun-like star. It means that many neutron stars, formed in ancient supernovae, have long since faded into radio silence by now. Those once young pulsars that danced rapidly at the dawn of our galaxy are today likely cold and quiet, indistinguishable from any other dark stellar corpse. This brevity makes the existence of pulsars even more special. They are brilliant, but short-lived beacons on the stage of galactic history. A pulsar, born shortly after the dinosaurs perished on Earth, would likely have already ceased pulsating by the time humans first looked up at the skies. In cosmic terms, pulsars are like fireworks, intense, mesmerizing, but fleeting. Once extinguished, the universe carries on around them, and they persist as faint echoes of a violent past, quietly moving through the galaxy without announcement. For example, the pulsar at the heart of the Crab Nebula, born from a supernova seen in 1054 CE, is still under 1,000 years old and spins about 30 times each second, emitting waves from radio to visible light to X-rays. By contrast, another pulsar that is, say, 100,000 years old might rotate only once per second, and its energy has dwindled so much that it can no longer shine in X-rays or visible light. It would be observable only as a faint radio source, if at all. Such is the dramatic change in a pulsar's vitality over relatively short spans of cosmic time. Somewhere in the darkness, that silent neutron star still drifts. It carries on its lonely journey around the galaxy, a faint echo of its former self. To an outside observer without special instruments, it would be all but invisible now, just a small, dense kernel of matter moving through the night. Countless such quiet behemoths are believed to populate the cosmos, unseen and unhearable. They are the hidden stars, radio silent and secretive. And indeed, for every pulsar we have heard singing across space, there may be hundreds more that whisper nothing at all. These extinguished pulsars do not announce their presence. Many were flung away from their birthplaces by the force of the supernova explosions that created them, and now they wander the galactic outskirts. Without the telltale ticking of pulses, a neutron star becomes a stealth object. It could float a few light years away, and we might never know, unless we stumbled upon its gravity or a faint X-ray glow from residual heat. Most of the galaxy's neutron stars are like this. Dark, quiet travelers, virtually indistinguishable from the void through which they move. They are everywhere and nowhere, a population of ghosts we can scarcely perceive. In truth, these silent remnants are far from rare. Astronomers estimate that the Milky Way is home to hundreds of millions of neutron stars born from past supernovae. Open. Maricopa, edu. By contrast, only a few thousand pulsars have ever been detected by our telescopes. This means the overwhelming majority of neutron stars lurk unseen. Some no longer emit detectable energy at all, while others might still beam faintly, but not in our direction. Over the long history of our galaxy, a new neutron star is born from a supernova every few decades. After billions of years, these additions have accumulated into an enormous unseen population. Even though we have only catalogued a few thousand, the invisible ones likely number in the hundreds of millions. The odds of Earth being in the path of any given pulsar's beam are low. Only a select few pulsars happen to sweep us with their cosmic lighthouse, while all the others remain hidden in darkness. To our instruments, they might as well not exist, even though they are out there. It's humbling to think about. Our surveys of the sky could miss literally hundreds of millions of these neutron stars. We know they must be there, but their light doesn't reach us, and so they slip by undetected in the vastness. These dark wanderers could be drifting even relatively close in the cosmic neighborhood without our knowledge. Without light or radio waves, a passing neutron star would announce itself only subtly, perhaps by tugging gravitationally on a nearby star, or bending the light from something behind it. Imagine one of these silent neutron stars gliding invisibly through space. It could traverse the outskirts of our solar system and remain unseen, except for the slight gravitational disturbances it might cause in the orbits of distant comets. No glow, no radio signal, just a heavy, unseen visitor slipping by. Only the force of its gravity gives it away, and even that is a whisper, unless you are very close. In the emptiness between the stars, such an object could pass within a few light years of Earth, and our telescopes might miss it entirely, masked by darkness. In rare cases, astronomers can catch such effects. By watching a background star's light warp as something massive drifts in front of it, they recently identified an invisible object likely to be a lone neutron star or black hole. For the first time, a neutron star may have been found not by its light, but by its gravitational footprint. It's a reminder that even in silence, these objects still make their presence felt through the fabric of space itself. Most, however, remain truly stealthy, simply circling the galaxy in darkness. This achievement required patience and precise observation. Using a telescope to notice a distant star's light, curiously bending and brightening, as if a hidden lens passed in front. Only something extremely dense and compact could cause such a gravitational lensing effect without being seen. In this case, it pointed to a dark neutron star roaming the void. It took decades of data and the sharp eyes of the Hubble Space Telescope to confirm it. Such detections are exceedingly rare, like catching the faint shadow of a ghost. For the vast majority of silent neutron stars, we lack the luck or technology to perceive them at all. Occasionally, however, the quietest of these stellar corpses won't stay completely hidden. Here and there, in the darkness, a ghostly sign may betray a neutron star that we would otherwise never know was there. A fleeting burst of radio waves with no apparent source, a faint patch of X-ray glow on the sky. These are the subtle apparitions that hint at the ghosts in the dark. For astronomers, Such unexpected signals were intriguing mysteries. A telescope might pick up a single loud heartbeat of radio emission from an empty-seeming part of the sky, leaving scientists wondering what could have shouted once and then fallen mute. Or an X-ray observatory finds a dim, persistent glow with no star visible at that spot in optical light. These are the clues that something exotic lurks unseen. Perhaps a neutron star that refuses to shine in the usual ways. In recent decades, more and more of these curious clues have emerged, gradually revealing a hidden menagerie of neutron stars that manifest as ghosts rather than lighthouses. In 2006, astronomers were puzzled to find brief bursts of radio energy that flickered on and off with no steady rhythm. Unlike ordinary pulsars that beat regularly, these mysterious sources might stay silent for long stretches, then suddenly emit a single burst, like a lone heartbeat echoing from a supposedly dead star. They came to be known as rotating radio transients, or RATs, and they are thought to be pulsars on the edge of extinction. It was as if a nearly extinguished star managed to cough up a last signal now and then. Imagine listening to the sky and hearing nothing for a long time. Then a single sharp knock sounds out of the darkness, and then silence again. Such an erratic signal made these objects hard to find. They hide in the quiet and only rarely whisper. When scientists realized what RATs could be, the idea was poignant. Perhaps an aged pulsar that has mostly died out, one that can no longer sustain regular pulses, is still spasmodically active. It's barely hanging on, flickering like an old bulb that sometimes flashes when you thought it had burned out. Not all pulsars announce themselves in radio waves. A few are like spectres seen only in other, higher energies. One famous case is a neutron star nicknamed Geminga, a name that sounds whimsical, but in a dialect of Italian, it literally means, "it's not there." Geminga earned this name because for a long time it was a puzzle. Astronomers detected high-energy gamma rays pulsing from its location, yet could find no radio signal at all. It was a pulsar that shone in gamma rays, while remaining practically silent in radio. Eventually, Geminga was recognized as a nearby rotating neutron star, one that somehow manages to beam chiefly in gamma and X-rays and not in the usual radio frequencies. In effect, its lighthouse casts an invisible light to our radio telescopes, making it a true ghost pulsar. To see Geminga, one must look at it with gamma-ray or X-ray eyes. In the radio spectrum, it might as well not exist. The realization that Geminga is a neutron star broadened our view of pulsars. It proved that some pulsars can hide from radio surveys, shining only in other forms of light, and thereby living up to that ghostly name. In addition to such individual cases, an entire small group of neutron stars has been found that emit virtually no radio waves. They are informally called the Magnificent Seven. 7 nearby isolated neutron stars that instead reveal themselves through a steady, faint X-ray glow. These stars spin only slowly, turning a few times each second, and they don't produce the flashy radio bursts of typical pulsars. Rather, they quietly radiate the residual heat from their surfaces. They are essentially cosmic embers, cooling, highly magnetized neutron stars that we see only because they are close by and still warm enough to shine in X-rays. In the radio spectrum, they are silent, giving no hint of their presence. True radio-quiet neutron stars hiding in plain sight. Each of these 7 emits only steady thermal X-rays, with perhaps a faint periodic flicker every few seconds, a far cry from the rapid ticks of a young pulsar. Their quiet nature confirms that not all neutron stars manifest as classic pulsars. Some simply cool and glow softly without ever producing strong radio beams. The Magnificent Seven gave astronomers a unique window into what a neutron star is like when it's just coasting through old age, peacefully radiating leftover heat. There are even neutron stars that start out in silence. In a few cases, when a massive star exploded, astronomers discovered a small X-ray source lingering in the supernova debris, a neutron star infant that isn't pulsating at all. These are called central compact objects, and they seem to be neutron stars born shrouded and quiet. One hypothesis is that after the supernova, a bit of stellar debris fell back onto the neutron star, burying its magnetic poles under a blanket of matter and choking off the pulsar mechanism. Only after centuries or millennia, as the debris clears and the field reasserts itself, might such a star light up as a pulsar. Until then, it remains a hidden ember at the center of a supernova remnant, a baby neutron star waiting in silence. Curiously, there is yet another kind of neutron star that usually hides its light in the radio spectrum, the magnetar. Magnetars are neutron stars with magnetic fields 1,000 times stronger than a typical pulsar. Under normal conditions, they can be quiet in radio, not pulsing like ordinary pulsars. But every so often, a magnetar reminds us of its presence with a tremendous flare of high-energy radiation. In 2004, one magnetar, halfway across the galaxy, released a burst of X-rays and gamma rays so intense that it briefly ionized Earth's upper atmosphere. Most of the time, these magnetars might appear as faint X-ray sources or be entirely undetected. Then, without warning, they erupt, a cosmic hiss or crackle breaking the silence. Such events are rare, but they show that even a silent neutron star may harbor fury beneath its quiet exterior. The magnetar's occasional outbursts are like a sudden flash of lightning from a dark cloud, illuminating the hidden power that lay unseen. In between bursts, a magnetar can be as elusive as any radio-quiet pulsar, giving no hint of its dramatic potential until the moment it strikes. What, then, is the ultimate fate of these quiet behemoths? Having shed their light and spent their energy, they do not disappear. They simply persist as inert, dark stars. Over many millennia, a neutron star will continue to cool. A newborn pulsar can be hotter than 10 million degrees, but without any new heat source, it inexorably loses its warmth, fading like a dying ember. After about 1 million years, a typical neutron star's surface may cool to roughly 1 million degrees. Given more time, it cools further, the feeble glow of its surface becoming harder to detect. Some older neutron stars we've observed have surface temperatures of only a few 100,000 degrees, still hot by human standards, but extremely cold and dim in cosmic terms. After millions upon millions of years, a neutron star could become so cool that it hardly radiates at all. At that point, it truly is like a cinder in the darkness, nearly invisible against the backdrop of space. No telescope we have today could easily spot such a frozen neutron star. It would blend with the night, radiating maybe just a trickle of infrared light, or nothing noticeable at all. The universe itself might eventually fill with these dark remnants as eons pass. Ancient neutron stars cooled to near invisibility. They would wander like ghost ships, carrying the record of their existence only in their immense gravity and dense matter. It's a quiet end state, from fiery birth in a supernova, to a brief life as a pulsar, to an eternity as a cold, dark sphere. For most neutron stars, this dark, quiet state is their twilight that lasts indefinitely. Yet, in rare circumstances, a lighthouse that went dark, can ignite once more. The key lies in companionship. If a neutron star orbits alongside another star, it may siphon gas from its partner. As this gas spirals onto the neutron star, it transfers energy and angular momentum, gradually spinning the dead pulsar back up to rapid rotation. With its rotation revitalized and fresh fuel heating its magnetic poles, the neutron star's beam can flicker on again. This rebirth often comes with a frenzy of activity. The infalling gas forms a spinning accretion disk around the neutron star, heating to extreme temperatures and emitting X-rays as it plunges inward. For a time, the once quiet neutron star becomes an X-ray beacon, powered by the feast of stolen matter. Then, as its rotation accelerates to hundreds of spins per second, the dormant radio beam can reactivate. A ghost pulsar is resurrected, transformed into one of the fastest pulsars in the galaxy. It's a remarkable second chance at life, granted by the close embrace of a companion star. Astronomers call such revived objects recycled pulsars, because the neutron star has essentially been given a second life. These often appear as millisecond pulsars, so called for their extremely short rotation periods, on the order of milliseconds. In its renewed youth, the neutron star's spin is incredibly fast, and its radio pulses extremely steady. It is as if a stopped cosmic clock has been wound up anew. The once extinct lighthouse shines again, albeit with a faster, steadier rhythm than in its first life. If we could voyage to one of these extinguished pulsars, the experience would be eerie and sublime. From afar, we might not notice anything unusual, until we began to feel its gravity. As our spacecraft drifted closer, the background stars would start to distort, their light bending subtly around an invisible mass. We would see no glowing sphere ahead of us, just a patch of sky where starlight warps and quivers. Only instruments would reveal the truth. A massive object, 10 kilometers across, directly ahead. Flying closer, the pull of gravity would grow intense, tugging at our ship. Time itself would slow imperceptibly in the strong gravity field. And yet, through all of this, the neutron star would remain nearly indiscernible to our eyes, a dark figure cloaked in the starry backdrop. If we were daring enough to orbit this silent giant, we might detect a faint heat emanating from its surface, especially if it still retains some warmth. The instruments could register a whisper of X-rays or infrared radiation. But to human senses, it would be darkness and silence. No crackling radio noise, no visible light, just the profound presence of something very heavy and very small exerting its influence on space. In the silence, one might reflect on the history of this object. It was once the core of a star. It once pulsed with energy, and now it simply exists, quiet and mysterious. Drifting above this neutron star, we would be in the company of a cosmic ghost, feeling more than seeing the reality of it. Such an encounter would underscore the haunting beauty of these quiet behemoths, formidable, enigmatic, and utterly still. In the end, a neutron star that has lost its pulse becomes a quiet monument to the forces of nature, tremendously dense, eternal in its inertia, yet all but undetectable. These lighthouses that went dark drift on through the Milky Way, silent but not insignificant. They still bear the mass of a star, still warp space with their gravity, and still hold within them the story of a star's death. Perhaps eons from now, one of these ghosts might encounter another star, or even another neutron star. And in that encounter, spark a new burst of activity, or even a final cataclysm that sends ripples through the cosmos. But for now, most simply roam quietly, unseen sentinels of an earlier age. Our universe is sprinkled with these quiet behemoths, each one a cold, small reminder of a star that once was. In their silence lies a profound mystery and serenity, a cosmic afterlife spent in the shadows between starlight and oblivion. In the autumn of 1967, beneath the quiet night sky at a radio observatory in England, a young astronomer noticed something odd. Her days and nights were spent scanning endless rolls of paper chart recordings, listening for whispers from the cosmos. She sat amidst a contraption of wooden posts and wires spread across a field, an unassuming radio telescope frame, more like an array of farm fences than a dish, spanning an area of dozens of tennis courts. It was crude but effective, built by hand to catch radio waves from the sky. Her task was laborious and mostly uneventful, but she remained vigilant, eyes on the wiggling ink lines that represented signals from space. Most of the time, the charts showed only noise and occasional blips from mundane sources like distant thunderstorms or passing satellites. But on one of those nights, a faint signal caught her eye. A tiny, regular blip that rose above the background static. It was an almost imperceptible waver, occupying only a fraction of an inch on many yards of paper chart, about a 1 in 10 million blip amid the noise. Yet there it was, repeating at a stable interval. It pulsed on the chart with uncanny steadiness, appearing and disappearing in a rhythmic pattern that no ordinary star or quasar was expected to produce. Intrigued, she marked the strange trace with a question mark and continued observing. Over subsequent nights, the mysterious signal returned, each time coming from the same patch of sky, keeping its place against the background stars night after night, and always with the same metronomic repetition, as if the universe itself had a heartbeat, quietly thumping out a steady pulse in the darkness. Then, in late November 1967, the signal burst forth unmistakably. A string of pulses, 1 1/3 seconds apart, marched across her recording. Jocelyn Bell Burnell, the 24-year-old graduate student who had spotted the anomaly, could hardly believe it. She alerted her supervisor, Dr. Anthony Hewish. Suspecting an equipment malfunction, they trained a second radio telescope at the same part of the sky to verify. At first, the secondary scope saw nothing, and the team grew anxious. But a few minutes later, right on schedule, the pulses appeared on its chart as well. This was no illusion. The mysterious beat was real, broadcasting from deep in space. Night after night, the pattern continued. A crisp blip every 1 1/3 seconds, far too regular to be random noise. The signal was so precise and so unlike any cosmic noise or quasar flare that the astronomers began to wonder if it might not be natural at all. Could it be a beacon from another civilization, a cosmic lighthouse built by alien hands? Half in jest, they tagged the strange source LGM-1, short for Little Green Men 1, acknowledging with a playful wink the astounding idea that had entered their minds. For a brief time, the observatory buzzed with nervous excitement at the prospect that perhaps, just perhaps, we were not alone, and someone out there was sending a radio hello. Privately, Jocelyn's supervisor and colleagues even debated how to handle the news if it were truly an alien beacon. One joked nervously that maybe they should burn the data rather than spark chaos. However, before any flying saucer fantasies could take hold, reality intervened. Only weeks later, the young scientists scoured her records and found yet another signal of the same type, a second celestial pulse, coming from a completely different part of the sky. This new pulse had a different rate, but it was unmistakably the same phenomenon. A rapid, periodic flash of radio energy, ticking like a second cosmic clock. The odds of two separate alien civilizations, on opposite sides of the sky, choosing the same moment and method to signal Earth, were virtually zero. The little green men hypothesis was quickly set aside. As Bell Burnell later remarked, it had to be some new kind of star, not seen before. In that moment, the mystery transformed into revelation. The team realized they had stumbled upon something unprecedented, a totally new type of astrophysical object that defied the catalogues of known stars and phenomena. This was a scientific revolution, a true eureka moment. In the weeks that followed, a total of 4 such pulsing sources were found, each beating out its own steady rhythm among the stars. Astronomers realized that only an object of extreme nature, something incredibly small, massive, and fast spinning, could produce such clockwork signals. It had to be the kind of remnant left after a star's death, the very collapsed core of a supernova itself. Indeed, theorists soon suggested that these might be rapidly rotating neutron stars, objects whose existence had been theorized decades earlier, but never observed until now. City-sized, ultra-dense stellar corpses sweeping beams of radio energy across space. In homage to their rhythmic flashing, these newfound objects were given a name that would become legendary in astrophysics. They were called pulsars, short for pulsating stars, the lighthouses of the cosmos. Far out in the void, the true nature of these pulsars reveals itself. Imagine a sphere about the size of a city, crammed with more mass than the sun, spinning on its axis at a tremendous rate. This is a neutron star, the final compressed core of a once mighty star, and a pulsar is a neutron star that behaves like a cosmic lighthouse. As it spins in the darkness, intense magnetic fields channel streams of radiation out from its north and south magnetic poles. These streams form 2 brilliant beams of radio waves, and sometimes visible light or X-rays, that swing around as the star rotates. If one of those beams sweeps across the Earth, an observatory will register a brief flash of radio energy, a pulse, with each rotation. To an astronomer tuning in, it's as though the star is blinking on and off regularly, sending out a steady cosmic Morse code from across the galaxy. Many other neutron stars likely remain hidden, their beams sweeping harmlessly past Earth. But when the orientation is just right, and that beam crosses our skies, we witness a flashing beacon that tells us a neutron star is there, spinning and sending its message out. But how does a star become a lighthouse? The answer lies in a dramatic transformation. When a massive star explodes as a supernova, its core collapses into a tiny ember, a neutron star, conserving the original star's angular momentum. Like a spinning ice skater who pulls in their arms, this shrunken star speeds up its rotation as it contracts. A star that once turned slowly can end up spinning many times per second after the collapse. In that moment, the material of the core is crushed to virtually inconceivable density. Imagine the mass of a star compressed into a city-sized sphere. In fact, if you jammed all the people on Earth into a thimble, it would weigh about as much as a thimble filled with neutron star matter. In the case of pulsars, the collapse also squeezes the star's magnetic field to colossal strength. The magnetic field of a pulsar can be billions or even trillions of times stronger than Earth's field, one of the mightiest magnetic forces in the universe. This whirling magnetic dynamo accelerates charged particles and sends twin jets of radiation shooting out along the magnetic poles. As the neutron star spins, those jets and the unseen magnetic poles whip around too. The beam of radiation is not aligned with the star's rotation axis, so it sweeps through space. It's exactly like a lighthouse on a lonely coast. The lamp stays lit, but only when the beam swings past our direction do we see a flash. Each pulse that reaches us is the result of one full rotation of the neutron star. In effect, we are witnessing the star's spin, turned into blips of light. The interval between pulses is the rotation period of the star itself, ranging from milliseconds to seconds long, depending on how fast the pulsar spins. Some pulsars turn lazily, perhaps once every few seconds, while others whirl with astonishing speed. At the center of the Crab Nebula, for instance, a pulsar spins about 30 times each second, casting rapid flashes of light and radio waves like a strobe in the cosmic night. Remarkably, this blinking star is the collapsed core of a supernova that was witnessed on Earth in the year 1054 AD, a brilliant guest star recorded by astronomers in China. Now, nearly a millennium later, that once bright star's heart still spins and pulses, a tiny lighthouse shining from the center of the Crab Nebula. And that is not even the fastest. Later, astronomers would discover millisecond pulsars, tiny stars spinning hundreds of times per second. Each of these stellar beacons keeps time with remarkable consistency, ticking away like the most precise of metronomes. In many ways, a pulsar's rhythmic flashing is like the heartbeat of a star that has died. The neutron star's core no longer burns with nuclear fire. It is a cold, collapsed remnant, yet it continues to beat through its rotation. Each pulse is a sign of lingering energy, the last remnant of the star's life ticking away. Listening to a pulsar's steady thump-thump in the radio data, one can't help but liken it to the faint heartbeat of a once mighty star, still echoing long after its fiery death. It's a haunting reminder, a stellar heart that continues to beat, even though the star itself has perished. Unlike a living heart, however, this cosmic heartbeat slows down over time. With each rotation, the pulsar radiates away a bit of its energy, acting as a brake on the star's spin. Over thousands of years, the pulses gradually grow slightly farther apart as the neutron star winds down, much like a spinning top gradually slowing on a table. In fact, most pulsars are very slowly losing speed, their heart rate decelerating imperceptibly with each passing century. After on the order of tens of millions of years, the star's pulse can fade entirely. By about 10 to 100 million years after its birth, a typical pulsar's spinning slows so much that it no longer sends detectable radio beats at all. The pulsar effectively flatlines. It becomes a silent, cold, stellar corpse, drifting through the galaxy as an invisible ember. Of all the neutron stars ever born in our Milky Way, an estimated 99% have already reached this quiet fate, no longer pulsating at all. Yet even as it steadily slows, the neutron star's heartbeat can be surprisingly resilient. And occasionally, it even skips a beat. Astronomers have observed that some pulsars experience sudden little hiccups in their rotation, events they've dubbed glitches. In 1969, for example, the Vela pulsar, a young neutron star in our cosmic neighborhood, was seen to suddenly speed up its spin ever so slightly, the first glitch ever recorded, which hinted that some internal shift had occurred within the star. In a glitch, the pulsar's rotation rate jumps abruptly, as if the star's heart momentarily raced ahead. After the glitch, the pulsation returns to its regular rhythm, but at a slightly faster pace than before. One leading explanation is that these glitches are caused by starquakes, a cracking adjustment of the star's ultra-dense crust that causes the neutron star to spin just a bit faster. Essentially, the rigid crust of the dead star shifts and settles, and like a skater pulling arms in for an instant, the star's spin speeds up minutely. These stellar palpitations are rare and subtle. The heartbeat of the pulsar might change by only a tiny fraction, but they reveal that even in death, a star can still be restless deep inside. In their heyday, pulsars serve as cosmic heartbeats, a tangible rhythm we can detect, bringing a dead star's story back to life through sound and signal. Over immense spans of time, that rhythm inevitably slows and fades. What remains afterward is a hushed remnant. The neutron star becomes a quiet behemoth, essentially undetectable to our instruments, its lighthouse beam extinguished. But while it beats, a pulsar gives us an intimate glimpse into the life after death of a star, a steady, unyielding heartbeat echoing in the silence of space until the final pulse falls quiet. At a radio observatory, the pulse of a distant pulsar can be transformed into sound, a steady series of ticks or beats that almost sounds like the clicking of an otherworldly clock. In fact, if you hook the radio signal to an audio speaker, you can hear a pulsar, a rapid series of ticks or chimes echoing in perfect time. A slow pulsar might sound like a deliberate knock, 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 while a fast one becomes a high-pitched hum or whir. Across the world, giant dish antennas and arrays of radio telescopes are constantly listening for these celestial metronomes. Each pulse arrives from across light years of space with exquisite regularity, allowing astronomers to measure time and space with astounding precision. In effect, pulsars are nature's finest clocks, their beats so consistent that they rival the accuracy of human-made timepieces. In fact, one astronomer described them as clocks dotted throughout the galaxy, each keeping almost perfect time amidst the cosmic void. Over the decades since that first discovery, astronomers have found thousands of these pulsars scattered across the Milky Way, each a tiny ticking beacon in its own lonely stretch of space. With such dependable rhythms, pulsars have become essential tools for probing the universe. By timing the arrival of each pulse with split-second accuracy, scientists can detect incredibly subtle effects. In the 1970s, a pulsar was found in a tight orbit around another neutron star, a binary pulsar system. Careful monitoring revealed that the pulsar's orbit was gradually shrinking, as if an unseen drag was at work. It turned out this was due to gravitational waves carrying away orbital energy, exactly as Einstein's theory of general relativity had predicted. The pulsar's clock-like pulses provided the proof. The two dead stars were spiraling together ever so slowly, their dance governed by the ripples in spacetime they emitted. This discovery was the first indirect detection of gravitational waves, earned a Nobel Prize, and opened a new chapter in astrophysics, all thanks to listening to a pulsar's heartbeat. Beyond tests of gravity, pulsars have even revealed new worlds. By watching for tiny variations in the timing of pulses, astronomers can detect the subtle gravitational tugs of orbiting planets. In 1992, this method led to the stunning discovery of the first exoplanets. Two Earth-mass planets circling a pulsar called PSR B257+12. These barren, blasted worlds were detected only because their small pulls caused the pulsar's heartbeat to wobble slightly. It was a striking confirmation that planets can exist even around a stellar remnant as extreme as a neutron star. And it marked the dawn of a new era in the search for worlds beyond our sun. Today, astronomers are using pulsars to explore even more profound cosmic phenomena. Over the past 15 years, international teams have turned a network of pulsars into a galaxy-sized observatory known as a pulsar timing array. By tracking dozens of millisecond pulsars scattered across the sky, they look for tiny deviations in the timing of the pulses, deviations that are the same for many pulsars at once. Such a collective wobble would signal that spacetime itself is gently vibrating on enormous scales. And indeed, in 2023, these teams announced the first tantalizing evidence that the universe is filled with a low-frequency gravitational wave background, a kind of cosmic hum reverberating through space. The telltale sign was a subtle synchronization in the ticks of far-flung pulsars. As giant gravitational waves washed through our region of the galaxy, stretching and squeezing space, certain pulses arrived slightly earlier or later than expected in a correlated pattern. It was as if the precise beat of multiple metronome stars all swayed together for a moment, responding to an unseen cosmic vibration. This pioneering measurement has given astronomers a new way to hear the behavior of colossal black holes merging in the distant universe, using the steady beats of neutron stars as their instrument. Pulsars have even been used as cosmic signposts for future explorers. When the twin Voyager probes were launched into interstellar space, each carried a golden record etched with a map of Earth's location. That map was based on pulsars. It showed the positions of 14 prominent pulsars relative to our Sun, with markings indicating their pulse frequencies. The idea was that any intelligent beings finding the probe could decipher the map. The unique periods of those pulsars would be like a galactic GPS, allowing our solar system's position and the era of launch to be triangulated. In essence, humanity used the steady beats of pulsars as our cosmic address label, confident that these lighthouses would shine for eons as unmistakable reference points. Closer to home, researchers are developing ways to navigate spacecraft by pulsars. Much like ancient mariners used the stars, future starships might use pulsars as reliable navigation beacons. By comparing the arrival time of pulses from multiple known pulsars, a spacecraft can determine its own location in space autonomously. In fact, experiments have already demonstrated that onboard X-ray detectors can lock onto pulsar signals and allow a craft to calculate its position with remarkable accuracy, potentially within a few kilometers, anywhere in the solar system. This pulsar-based navigation concept could one day guide astronauts through the deep void without relying on Earth, using the cosmos's own lighthouse network to chart their path. And yet, for all we have learned by listening to pulsars, these lighthouses in the void are not the whole story of neutron stars. In the cosmic sea, there are other dead stars that do not beam so helpfully. Stellar corpses whose signals are intermittent or entirely absent. Some neutron stars flare up in unpredictable bursts of high-energy light, while others remain dark and quiet, detectable only by their gravitational tug or a faint glow. These are the silent pulsars and hidden neutron stars, the quiet behemoths that give this documentary its name. As we continue our journey, we will venture into the realm of these elusive objects, exploring how even in their silence, they reveal new facets of the extreme physics and mystery of collapsed stars. The cosmic story grows ever deeper and stranger, waiting for us to listen beyond the pulses into the silence that follows. This success has opened the door for future deep space missions to navigate autonomously using pulsars. One can imagine a spacecraft cruising through the outer solar system, or even between stars, using an onboard pulsar catalog and X-ray telescope to constantly fix its position. No need for real-time updates from Earth. The ship can read the cosmos's own signposts. It's a profound thought. A dead star's heartbeat guiding a living spacecraft across the void. In fact, the very first confirmed exoplanets were discovered around a pulsar, PSR B257+12, in the early 1990s by noticing subtle variations in the pulsar's pulse arrival times. That discovery was an unexpected one, finding planets in the hostile environment of a pulsar system. But it showcased how incredibly sensitive pulsar timing can be to gravitational tugs. If a planet as small as a few Earth masses orbits a pulsar, the timing of the pulses shifts enough that we can detect it from Earth. Thus, pulsars have even helped unveil new worlds, acting as cosmic detectives for phenomena that would otherwise remain hidden. Pulsars have guided science in other, more abstract ways as well. They've been used to confirm aspects of Einstein's general relativity under conditions far more extreme than we can create on Earth. The Hulse-Taylor binary pulsar was one example, verifying the energy loss due to gravitational waves. Another is the remarkable double pulsar system, PSR J0737-3039a-B, discovered in 2003. Here, two neutron stars, both observable as pulsars, orbit each other every 2.4 hours. With two clocks in orbit, this system provided an unprecedented testbed for relativity. Over years of observation, every prediction of general relativity, such as the gravitational redshift, time dilation, and orbital decay due to gravitational waves, was confirmed to extraordinary precision, agreeing with theory to within a fraction of a percent. In these cases, pulsars are both the experiment and the measuring apparatus, allowing us to probe nature's laws under conditions of intense gravity and velocity that no laboratory could replicate. It is a beautiful irony that objects born from chaos and destruction can become the universe's most steadfast beacons and clocks. The same neutron star that was created in a supernova explosion, one of the most violent events in nature, can later spin quietly in the darkness, flashing a clockwork beacon that we use to navigate and explore. From drama to diligence, the life of a neutron star covers a remarkable range. Through pulsars, we have found a cosmic ally in exploration and understanding. With their help, we measure the shape of spacetime, we map our location in the galaxy, and we keep time on scales both human and astronomical. As our journey through the realm of neutron stars and pulsars comes to a pause, we're left with a sense of awe at the richness of their story. We began with their violent birth and followed through to their quiet, steady ticking. These quiet behemoths, once engines of supernovae and the source of gamma-ray bursts, become gentle guides in the cosmic sea. They remind us that even in a universe full of cataclysms, there are lighthouses in the dark and clocks in the silence, steadily ticking away the eons. Our exploration does not truly end here. Each discovery about neutron stars seems to raise new questions. The cosmic choreography of binary pulsars and the cosmic echoes they produce in gravitational waves and radio pulses continue to intrigue and inspire scientists. We will keep listening to the whispers of spacetime and to the ticking of pulsars, for they carry messages from the universe's most hidden corners. Even now, as we gaze up at the night sky, those pulsars are out there in the dark, unseen pinpoints spinning with clockwork precision. They remind us that even in the vast silent void, there is order and rhythm. It is comforting to know that in the silent expanses of space, such reliable beacons exist, a reminder that we are never truly alone when we navigate the cosmic ocean. All we have to do is listen and let their rhythm guide us onward. In the stillness of the cosmic night, two ancient stars move as one. These are neutron stars, collapsed cores of once mighty suns, and though each is only the size of a city, they carry more mass than an entire sun. Imagine two spheres no wider than 20 kilometers across, yet so heavy that a mere teaspoon of their substance would outweigh a mountain. They drift in the darkness, caught in each other's gravitational embrace. Circling silently, they perform an endless cosmic waltz, their motion so subtle and slow that millennia pass with only the slightest change. No light remains to shine brightly. They glow only faintly with residual heat, nearly invisible against the blackness of space. And so they spin around a shared center, bound together by the gentle but unyielding tether of gravity. In this silent dance, time itself seems to stretch, a slow ballet in the quiet of an eternal night. Inside each neutron star, conditions defy imagination. The density and pressure are so extreme that the very structure of ordinary atoms collapses. Electrons have been crushed into protons, forming neutrons. The entire star becomes a single gargantuan atomic nucleus. Matter in this ultra-compressed state behaves in strange and exotic ways. Deep inside, nuclei meld together and particles flow in quantum unison. The interior might even be a superfluid ocean of neutrons, or perhaps something even more exotic, like a soup of quarks freed from their bonds. We do not know for certain, for such conditions lie far beyond our earthly experiments. Yet out of this crushed, ultra-dense matter, a remarkably stable star is formed. A neutron star no longer shines like an ordinary star, but instead marks time with its rotation and immense gravity. It is an almost indestructible sphere at the edge of physics, as we understand it. A quiet titan made of the stuff of nuclear nightmares, now peacefully orbiting its twin. Long ago, these two neutron stars were born together, likely as a pair of brilliant suns that lived out their lives side by side. In their final throes, each star died in a supernova explosion, blasting its outer layers into space and leaving only a dense core behind. Against all odds, the two cores remained gravitationally entwined even after those cataclysms. Their orbits may have wobbled from the force of the explosions, but the partnership survived. Now the twin neutron stars continue to circle each other as they have for eons. From a distance, they would appear as faint, darkened embers gliding in tandem against a backdrop of stars. There is no fanfare to their motion, only the unseen pull they exert on one another and the unseen energy they shed into space. Round and round they go, an endless nighttime duet. At first their orbit is wide and leisurely, perhaps taking long hours or days to complete a single circuit. With each revolution, however, a subtle energy drains away from the system. The two neutron stars stir the fabric of space-time itself as they move, sending faint ripples outward. These ripples are gravitational waves, silent tremors in the very structure of space and time, carrying off a tiny fraction of the binary's energy. Barely noticeable at first, over countless millennia, these gravitational waves act like a gentle brake, drawing the stars ever so slightly closer on each orbit. Like concentric rings spreading across a pond after a pebble's drop, these space-time ripples race away at light speed. They carry the news of the stars' slow dance out into the universe, though by the time this whisper of a wave reaches far-off worlds, it is unimaginably faint. Drifting through the ages, the neutron-star pair spirals gradually inward. What began as a sedate orbit now imperceptibly quickens. Thousands, then millions of years pass, and the distance between the two stars shrinks, meter by meter, kilometer by kilometer. Gravity's grasp grows stronger as they draw nearer, pulling them faster along their orbital path. Still, all of this unfolds in perfect silence. No sound can travel in the vacuum between them, and no distant observer would notice anything unusual yet. But if we could somehow listen to the fabric of space itself, we would hear the gravitational song of this system increasing in pitch and intensity. It begins as a deep, low hum, the bass note of their far-apart orbit, and over the eons it rises in frequency, a cosmic crescendo building as the dance hastens. In essence, the gravitational waves are like a steadily rising chirp, growing higher and louder to a gravity wave listener as the neutron stars orbit faster and faster. Over countless ages, their dance persists, nearly unchanged to any outside view. But at last, the fatal moment approaches. What had been a gradual pirouette for millennia is about to become a sudden finale. The end of this cosmic ballet, long foreseen by physics, draws near in a burst of violence. As the neutron stars approach one another more closely, their orbital period, once measured in hours, dwindles to minutes, then seconds. In their final orbits, the two tiny giants whirl around each other dozens of times each second. Their speed is incredible. Each star becomes a blur, moving at a significant fraction of light speed as they loop around their common center. The very structure of each star begins to feel the strain of this furious motion. Tidal forces deform them, stretching each star into an egg shape and raising enormous tidal bulges on their surfaces. Under such extreme stresses, the crust of each neutron star may crack and shift. In those last instants, bits of neutron-rich matter could be flung outward, droplets of star stuff tossed into space like water from a wildly spinning wheel, only to be pulled back in moments later. The gravitational waves they emit now rise to a frantic crescendo, ringing out through space like the final peal of an enormous cosmic bell. In a fraction of a second, the dance reaches its climax. The two neutron stars meet at last. They collide and merge in a violent embrace, ending their ancient orbit forever. At the moment of impact, the energy released is colossal. For a brief instant, as they slam together, there is a burst of radiation so intense that it lights up the darkness of space. Two ultra-dense bodies, each more massive than the sun, join together and unleash a flood of energy. A flash of gamma rays, the highest energy form of light, erupts from the collision point, beaming out in tight jets along the magnetic poles of the newly formed object. This gamma ray burst is astonishingly bright, though it lasts only a second or two. Across the universe, any instruments attuned to such high energies would register a sudden, intense pulse, a fleeting cry of photons announcing that two stars have become one. For an eye blink of time, this burst outshines an entire galaxy's worth of normal stars. It is a cosmic beacon, a shout into the void, heralding the moment of coalescence. At the same moment, an invisible flood of neutrinos, ghostly, nearly massless particles, streams out from the merging stars in all directions. In fact, neutrinos carry away a tremendous portion of the energy of this event. These ghost particles hardly interact with matter at all. They fly straight through the debris and the stars themselves, as if everything were transparent. Though nearly undetectable, they are a significant part of the cosmic explosion, rushing outward into space along with the gravitational waves and gamma rays. A storm of neutrinos passes any nearby location mere seconds after the merger, utterly silent and invisible, but an important release valve for the incredible energies involved. Moments after the collision, a new light begins to bloom around the merged stars. What had been two compact objects has now become a single, highly excited mass surrounded by a cloud of superheated debris. This debris was flung out during the final smash, and now it expands rapidly into space. Astronomers call the glow of this expanding debris a kilonova, an event less luminous than a full-fledged supernova, but still vastly brighter than an ordinary nova. In the immediate aftermath, the debris cloud shines a fierce blue-white, hot as the core of a star. It balloons outward, unimpeded, doubling in size in mere hours. Within a day, it can span billions of kilometers, an expanding sphere of incandescent gas larger than an entire solar system. As the kilonova's fireball grows, its light evolves. The initial brilliant blue glow begins to soften and redden as the cloud of ejected matter cools and thins out. What was once a blinding flash becomes a warm, ruddy luminosity over the course of days and weeks. To an observer at a safe distance, it might appear as a sudden new star in the sky, first with an intense bluish glare, then fading through gold into a dim red ember before disappearing from view. These colours are clues to extraordinary events transpiring within the expanding debris. In the heart of that spreading cloud, an act of cosmic alchemy is taking place. The collision has torn out huge quantities of neutron-rich material from the stars and flung it into space. In these extreme conditions, atomic nuclei are bombarded by an avalanche of neutrons. They rapidly absorb these neutrons and then undergo radioactive decays, transforming into heavier elements. This brief, intense sequence of reactions is known to physicists as the R process, and it is a crucible for creating some of the universe's heaviest elements. As the ejected matter cools and transitions from blue to red, it is forging new atomic nuclei. Gold, silver, platinum, elements heavier than iron, which normal stellar fusion cannot produce, are synthesized in great quantities. The bluish tint of the early kilonova light comes from the presence of lighter, hotter elements forming initially. The later deep red glow is a sign that heavy, neutron-rich elements dominate the cooling cloud, since such elements tend to block blue light and let only red wavelengths escape. It is awe-inspiring to realize that something as precious as gold is being minted in that chaos. The beauty of a golden ring on a finger originates from the fury of colliding stars. As incredible as it sounds, scientists estimate that a single neutron star merger can manufacture an immense treasure of heavy elements. The amount of gold alone produced in that one collision is thought to be equivalent to many times the mass of the Earth. Even more platinum, rarer than gold on Earth, is created, along with a host of other heavy metals. Newly formed atoms of elements like iodine, uranium, and xenon are cast out into interstellar space, riding along in the expanding debris cloud. The cosmic treasury is enriched by the wreckage of these two stars. As the kilonova fades from sight, its legacy endures in the enriched matter it leaves behind. What were once two ultra-dense neutron stars have become a diffuse nebula of heavy elements and stellar ash. At the center, the combined mass of the two stars has collapsed into a new entity. It may be a larger neutron star, at least temporarily, or, if enough mass gathered, it will have crushed itself into a black hole. In many cases, the merged core is so heavy that gravity wins outright, and a black hole forms almost immediately. If so, it's as if a trapdoor in space opened at that spot. The remnant vanishes behind an event horizon, and not even light can escape the region now. Any remaining debris around the center might briefly swirl into an accretion disk, heating up and launching additional jets of particles, giving one last burst of high-energy radiation. In other cases, if the merged mass is just below the tipping point, it might remain for a time as an extremely massive neutron star, spinning rapidly and shedding energy until it too eventually collapses into a black hole. Either way, the original neutron stars that danced together for billions of years are gone, transformed into a new state of being. Yet, paradoxically, from this violent ending comes the promise of new beginnings elsewhere. The heavy elements blown out by the kilonova will eventually mix into the surrounding interstellar gas. In time, that enriched gas will cool, clump, and form new stars and planets. The gold in a wedding ring, the iodine in a human thyroid, the uranium deep in Earth's crust. These may all trace their origin to ancient neutron star collisions that seeded our region of space long before the Sun existed. Some clues even suggest that one such merger happened not far from where our solar system was forming. Radioactive isotopes found in primitive meteorites hint that a neutron star collision may have occurred a few tens of millions of years before our Sun was born, sprinkling freshly forged heavy metals into the very cloud of gas and dust that collapsed to create the Sun and planets. The cosmos truly recycles its matter through such cataclysms. In a very real sense, we ourselves carry pieces of this cosmic story. Some atoms in our bodies, perhaps the iodine in our diets or the gold in our fillings, were forged in the crucible of a neutron star merger. The universe used fire and fury to shape the elements that would one day make life possible. It is a humbling thought that the jewelry we treasure and the technology we depend on are made of atoms born in the death throes of stars. While the explosive finale of the binary neutron stars is one dramatic chapter in the saga of these quiet behemoths, not all neutron stars meet such an end. The universe is sprinkled with countless solitary neutron stars as well, those that remain after supernovae but never find a companion to merge with. Many of these lonely stars simply cool and fade over time, practically invisible, like cosmic embers slowly losing their glow. But some neutron stars continue to play an active role in the cosmos without the need for a partner. These are the ones that spin rapidly and shine not in steady light, but in flashes. We call them pulsars, and they are cosmic lighthouses and timekeepers. Picture a single neutron star adrift in the darkness after its birth explosion. It is an ultra-dense sphere about 20 kilometers across, containing more mass than 500,000 Earths. It may be cooling and dim, unseen in most wavelengths, but it is far from inert. If this neutron star is spinning, as many do, and possesses a tremendously strong magnetic field, trillions of times stronger than Earth's field, it becomes something extraordinary, a pulsar. From its magnetic poles, twin beams of radiation begin to shoot outward, powered by the star's rotation and magnetic fury. These beams are like cosmic searchlights sweeping through space as the star spins. If one of those beams crosses Earth's line of sight, we perceive a pulse of light or radio waves with uncanny regularity. When pulsars were first detected by radio telescopes in the late 1960s, their signals were so precise and regular that they puzzled astronomers. Jocelyn Bell, a graduate student in England, noticed a series of equally spaced blips in her radio survey data, pulses arriving every 1.3 seconds like clockwork. These pulses were so perfectly timed that for a brief while, the team half-jokingly dubbed the source LGM-1, short for Little Green Men 1, wondering if it could be an artificial beacon from an alien civilization. It soon became clear, however, that this was no alien signal, but a new kind of natural phenomenon. They had discovered a rapidly spinning neutron star flashing its beams toward Earth, the very first known pulsar. If you could stand near a pulsar, protected somehow from its deadly radiation and intense gravity, you would witness one of the universe's great light shows. The neutron star itself would be a sphere barely the size of a city, but containing the mass of a sun. It would spin on its axis at an incredible rate. Some pulsars turn only once per second, but others whirl hundreds of times each second. As it spins, its intense magnetic field, anchored in the star and spinning with it, sends out focused beams of electromagnetic radiation. Each beam sweeps across the sky like the spotlight of a lighthouse. To a distant observer aligned just right, the pulsar appears to blink on and off with each rotation as the beam crosses their line of sight. To any such observer, these blinks arrive with absolute regularity, like the steady ticking of a clock. In fact, if we convert a pulsar's radio signals into audible clicks, we would hear a steady rhythm. A slower pulsar might sound like a deliberate metronome. Tick, tick, tick. Each pulse separated by seconds. A millisecond pulsar, spinning hundreds of times a second, would merge into a continuous, high-pitched hum, like a far-off mosquito whine or a swiftly beating drum. Each pulsar has its own unique voice and tempo, in this sense, a cosmic heartbeat echoing through the void. Pulsars are truly nature's timekeepers. A stable pulsar's beat can be as reliable as the ticking of a finely crafted clock. In fact, over long periods, certain pulsars rival the precision of atomic clocks, the gold standard of time measurement here on Earth. These stellar remnants rotate so steadily that their spin rate might drift by only a few millionths of a second over many years. They do gradually slow down, almost imperceptibly, as they radiate energy into space, and occasionally they undergo small glitches, sudden tiny jumps in rotation speed when the star's crust cracks and shifts. But apart from those minor hiccups, a pulsar's rhythm is astonishingly regular. If a pulsar spins 30 times a second today, millions of years from now, it may still be spinning nearly 30 times a second, only marginally slowed. This incredible steadiness allows pulsars to serve as cosmic clocks, keeping time across the vastness of space. On the flip side, the extreme precision of pulsar signals makes them excellent cosmic sensors as well. Any slight disturbance to a pulsar, say the gravitational tug of an orbiting object, will reveal itself as a minute change in the arrival time of its pulses. If a pulsar has a companion, whether another star or even planets, it will wobble slightly as they orbit their common center of mass. That wobble causes the pulsar's pulses to arrive a bit early or late in a regular pattern. By measuring those tiny timing variations, astronomers can infer the presence of orbiting bodies. Indeed, the very first planets ever discovered outside our solar system were found around a pulsar in 1992, detected by the telltale dance they induced in its pulse timings. It was an astonishing revelation. Planets circling a dead star, revealed only because the pulsar's ticking is so steady that even a slight perturbation could be noticed. Astronomers have learned to use these pulsar clocks in other creative ways too. Decades before we ever directly detected gravitational waves on Earth, a pulsar provided indirect proof that these ripples in spacetime exist. In the 1970s, a neutron star binary was discovered in which one member was a pulsar. By timing that pulsar's blinks, scientists could track the orbit of the two neutron stars with exquisite precision. They noticed the orbit was shrinking ever so slightly, exactly as Einstein's general theory of relativity predicted it should if gravitational waves were carrying energy away. Year by year, the pulsar's signals indicated the stars were drawing closer together, right on schedule with relativity's equations. It was a triumph of careful timing and physics, a hearing of gravitational waves in effect, decades before any instrument could directly sense them. That discovery earned the researchers a Nobel Prize and gave us confidence that neutron star binaries do in spiral and will eventually merge, as we later saw with kilonovae. Beyond testing the limits of physics, pulsars have also become essential tools for navigation and exploration, a guiding light for future cosmic journeys. On Earth, for centuries, travelers used the stars to find their way. Now, pulsars promise a natural GPS that works anywhere in the galaxy. Each pulsar has a unique spin period and pattern of pulses, effectively serving as an identifiable beacon in space. It's akin to how ancient mariners used the fixed stars to navigate oceans. But here, our guide stars are pulsars, and the ocean is interstellar space. By comparing the timing of pulses from 3 or more known pulsars, a spacecraft can triangulate its own position, much as a navigator uses multiple lighthouse bearings to fix a location at sea. This idea is not just theoretical. Space agencies have already begun experimenting with pulsar-based navigation. In 2018, an instrument on the International Space Station successfully determined its orbit using X-ray signals from millisecond pulsars. Over a few days, it pinpointed the station's position to within about 5 kilometers, purely by reading the pulsar beats, a proof of concept galactic positioning system. In that moment, what once was science fiction became reality on a small scale. A spacecraft found its location by the light of dead stars. Pulsar navigation holds great promise for the future. Imagine a ship voyaging far from Earth, beyond the range of our familiar GPS satellites. In deep, interplanetary space, or even on the journey to another star, the spacecraft can still know where it is by listening to the cosmos. A deep space vessel equipped with special detectors can tune into the periodic X-ray or radio flashes of distant pulsars. No matter where it travels, behind the sun or out in the Oort cloud, the timing of those pulses remains steady and true. By comparing pulse arrival times from a few well-chosen pulsars, the ship's onboard computer can pinpoint its coordinates without needing Earth-based signals at all. The pulsar beacons cannot be jammed or turned off. They are as steady as nature itself. Spacefarers of tomorrow might chart their course by these distant lighthouses, confident that the guiding beacons will never fail as long as the stars endure. It's poetic to think that even before we harnessed pulsars for our own navigation, we inscribed their patterns into a message for unknown travelers. When the Voyager probes were launched in 1977 to journey beyond the solar system, each carried a golden record with a pulsar map etched onto its cover. This diagram of lines radiating from a point shows the location of our Sun relative to 14 prominent pulsars scattered across the galaxy. Each line is labeled with the pulsar's unique pulse frequency in binary code, using the fundamental time unit of a hydrogen atom's transition. Any spacefaring civilization that discovers the Voyager record could use that map to locate our solar system. Each pulse's period serves as a kind of galactic address. By comparing the measured periods of pulsars to those engraved on the map, which would have drifted slightly over time, the finders could even deduce how long ago the Voyager spacecraft was launched. In using pulsars as our cosmic signposts, we essentially said, "Here is our home in the universe, written in the universal language of time and stars." Thus, pulsars are not just astronomical curiosities, they are bridges across space and time. Their steady beats link far-flung corners of the galaxy, and their predictable rhythms carry information that navigators and astronomers can use. By monitoring many pulsars spread across the sky, scientists have effectively turned our entire Milky Way into a giant gravitational wave detector. Each pulsar's reliable beat acts like a metronome. If a long wavelength gravitational wave perhaps from the slow merger of supermassive black holes in distant galaxies, washes over us, it will very slightly disturb the timing of those beats. By observing an array of pulsars over years and looking for subtle correlated shifts in their pulse arrival times, astronomers can detect the gentle stretching and squeezing of spacetime from such waves. Indeed, recent observations have reported the first hints of a background hum of gravitational waves permeating the universe, likely the combined murmurs of countless distant black hole mergers. This incredible feat was accomplished only by listening to the steady ticking of dozens of pulsars spread across the sky. From the catastrophic collision of two neutron stars to the gentle ticking of solitary pulsars, we see the dual nature of these quiet behemoths. They are both destroyers and creators, both violent and steadfast. In one moment, two neutron stars can merge and forge gold through a stupendous explosion. In another moment, a lonely neutron star can spin in silence, serving as a cosmic lighthouse and clock. Largely, they remain silent in an audible sense. No sound reaches our ears from these distant events, yet they speak volumes through their gravitational echoes, their flashes of light, and the steady beat of their pulses. They choreograph cosmic dances and emit cosmic music that we are only now learning to hear and interpret. As we drift in thought through these cosmic scenes, the spiraling dance of binary stars, the radiant bloom of a kilonova, the pinpoint flicker of a pulsar across light years, it becomes clear that this story is far from over. Each discovery leads to new questions. What exotic states of matter might hide in the core of a neutron star? How intense can a neutron star's magnetic field become? As we glimpse in the occasional flares of magnetars, those temperamental cousins of pulsars, what other messages might be encoded in the timing of pulsars that we have yet to decipher? There is so much more to learn and wonder about. In truth, the tale of neutron stars and their silent pulsars is still being written. With each new observation and each new insight, another page of the cosmic chronicle turns. For now, we leave this chapter of the journey without a definitive conclusion, knowing that the dance continues and more cosmic whispers await us in the darkness. The quiet behemoths, those neutron stars and silent pulsars, spin on in the endless night, their presence marked by gentle pulses and distant echoes. And we, the observers, will keep listening. Each faint pulse, each ripple in space-time, beckons us onward into the next part of the story, as we continue our exploration of the deep and ever-mysterious universe. In the silent depths of space, two faint stars circle one another in a gravitational embrace. These are no ordinary stars, but the remnants of giants. At least one, if not both, has collapsed into a neutron star. They orbit a common center, locked together by an invisible tether of gravity. With each passing second, they trace a cosmic waltz, moving in synchrony through the darkness. Their dance is graceful, yet unyielding, a rhythm set millions of years ago when they first became partners in the void. Not all neutron stars roam alone. Some are born as twins, forged from the cataclysmic deaths of two massive stars that once lived side by side. After each supernova explosion, what remains of those stars can stay bound, forming a binary neutron star system. In such a pairing, two city-sized, ultra-dense stars whirl around each other. Imagine them as cosmic dancers, dark, tiny spheres, no larger than a city, yet each with more mass than our sun. Separated by a distance, perhaps only a few times that between Earth and the Moon, They swing around at tremendous speeds. In some cases, one might complete an orbit in just a few hours. The pull of their gravity on one another is intense, slingshotting them through space in tight loops. From afar, to an observer with the right instruments, one might see the telltale flicker of a pulsar in the pair, flashing at steady intervals as it spins. The other might be another pulsar, or a silent neutron star companion, its presence revealed only by the effect on its partner's motion. Their movement is a delicate interplay, perfectly choreographed by gravity's laws. Each star falls toward the other, drawn by its mass, but their sideways motion keeps them perpetually circling rather than colliding, at least for now. They spin around a shared center of mass, like two dancers holding hands and rotating around a point between them. One moment, one star is closer, tugging a bit stronger. The next, it sweeps outward slightly as the other comes near. Over long periods, their orbits might be elongated, tracing ellipses that bring them periodically nearer and farther apart. But here, the two partners are of nearly equal weight, performing a celestial duet in a tight orbit. In this silent dance, there is no friction, no sound, only the vacuum and the faint whisper of forces at play. According to Einstein's general theory of relativity, as these massive bodies orbit, they disturb the fabric of spacetime itself. With every twist of their orbit, they send out tiny ripples in spacetime known as gravitational waves. These ripples carry energy away from the system, radiating into the cosmos like concentric waves in a pond after a stone is dropped. Each wave is incredibly weak by the time it reaches distant observers, but the energy it carries is stolen from the orbital dance. Bit by bit, this loss of energy causes the dance to change. The stars draw infinitesimally closer together, their orbit tightening over time. The change is fantastically slow, almost imperceptible over human timescales, yet inexorable. Years pass, and then centuries and millennia, and the dance continues. To the stars themselves, nothing seems different. They have circled each other millions of times, and will circle millions more. But gradually, the effect of those gravitational wave whispers adds up. The orbit that once might have taken, say, 8 hours to complete, now takes a fraction of a second less. In a year, perhaps only microseconds of time are shaved off each orbit, tiny differences that could only be noticed by the most precise measurements. Indeed, astronomers observing a binary pulsar have found exactly this. The orbital period changing by only a few parts in a trillion, matching precisely what relativity predicts. It is as if the dance is accelerating ever so slightly, the partners drawing closer in an ever-tightening spiral. This slow tightening is destiny at work. The neutron stars are fated to meet someday, though that day might be far in the future. For now, they remain distinct, whirling around each other in a stable routine that could endure for hundreds of millions of years. If we could watch their entire lives in fast forward, we would see the spiral quicken dramatically only in the final moments. But from our human vantage, decades or centuries mean almost nothing to their long tail. We simply marvel that two such massive, exotic objects can pirouette around each other so consistently and for so long. Each time the pulsar companion swings toward us, we catch its pulse a fraction of a second sooner than expected. When it swings away, the pulse arrives a bit late. These tiny timing shifts are the heartbeat of the orbit, letting us listen to the dance from across light years. Through such observations, scientists first learned about this slow cosmic waltz speeding up. The binary pulsar's ticking has served as a clock to reveal what our eyes cannot directly see, the energy slipping away invisibly as gravitational waves. For eons, nothing dramatic disturbs the pair. They circle silently, unseeable to the naked eye, lost in the dark of space, except for the rhythmic beacon of the pulsar's signal. Two tiny, dense stars locked in their private whirl. It's a picture both enchanting and slightly ominous. They are bound by a mutual fate, sealed the moment they were born together out of stellar death. They continue their ballet across the ages, gradually drawn closer by an unrelenting cosmic tide. The dance of these binary stars is a thing of beauty, but it cannot last forever. Someday, perhaps hundreds of millions of years from its beginning, the music will crescendo to a finale. The two partners will come so close that their final act can only be a union. Gravity, which kept them apart and in orbit for so long, will finally pull them into each other's embrace. Tonight, however, they remain in their ancient dance. In our mind's eye, we leave them in this quiet performance, a binary neutron star system twirling in the silent darkness, sending gentle ripples through space-time with every turn. Unbeknownst to them, distant civilizations might someday detect those ripples and wonder about the dancers that caused them. And indeed, in our own time, humanity has begun to detect such whispers. But before we delve into that revelation, let us imagine what will eventually happen when the slow waltz of our two stars reaches its inevitable, dramatic finale. At last, the fateful moment arrives. After countless millennia of circling, the two neutron stars can no longer resist their mutual pull. Their orbits have shrunk to mere minutes, then seconds. In those final orbits, they whip around each other frantically, moving at a significant fraction of the speed of light. The stars themselves are deformed by enormous tidal forces. Each neutron star raises tides on the other, not of water, but of star stuff, pulling matter into elongated bulges. In the last few blinks of time, those bulges grow and stretch between the two. A stream of neutron-rich material may even fling outward as the stars skim each other's surfaces. And then, inevitably, the two heavy spheres collide. In that instant, unimaginable violence erupts. Two ultra-dense cores slam together at relativistic speeds. For a brief moment, the combined mass vibrates and contorts, sending a powerful burst of gravitational waves racing outward. If we could somehow hear gravitational waves, we would perceive a sharp chirp, a rapidly rising tone as the merger happens. The fabric of space-time itself rings from this event, broadcasting the news of the collision across the universe. Almost simultaneously, a flash of high-energy gamma radiation spears out. This is a short gamma-ray burst, lasting only a second or two, but in that blink, it outshines entire galaxies. Beams of gamma rays shoot from the poles of the merging stars, driven by ultra-fast jets of matter blasting outward along the rotation axes. Should those beams cross Earth's path, our satellites and observatories would register a sudden, intense flash of gamma rays from what was previously an unremarkable point in the sky. But the drama is not done. The merger has created an enormous volume of superheated, neutron-rich debris around the collision site. What were once the solid crusts and dense cores of two stars are now a smashed-together cloud of exotic matter. Neutron star material, normally bound by incredible gravity, is flung outward, freed by the collision's fury. Within seconds, this ejected material forms an expanding shell of debris rushing into space. It's an inferno of liberated neutrons and newly formed atomic nuclei. As this cloud expands, it begins to shine. The heat and radioactive decay of the freshly forged elements produce a brilliant display, the kilonova. At first, the kilonova blaze burns with a fierce blue-white light. The temperatures are extreme, and lighter elements in the mix emit high-energy photons. The expanding fireball glows blue-hot for a short time, radiating energy across the spectrum. But as hours and days pass, the light from the explosion evolves. The debris cloud is swelling and cooling. Within a day or two, the brilliant blue hues shift toward a rich red. Heavier elements that have formed in the chaos start to dominate the cloud, blanketing the fireball and giving the light a deeper, redder cast. The glow remains intense, but now has the color of embers at dusk, as those new elements undergo radioactive decay, powering the fading fire. From a great distance, an astronomer watching through a telescope would see a new pinprick of light in a galaxy where none was before. It might not rival the absolute brightness of the largest supernovae, but it is still a significant new light in the sky, rising to a peak brightness over a matter of a day or two. This is the kilonova, the combined light of all those heavy elements being freshly born and then decaying. It is far more luminous than a typical nova, on the order of 1,000 times more energetic, hence the name kilonova. Over the next days and weeks, this transient starburst will fade away, disappearing back into the darkness. But for a short time it shines as a beacon, telling a tale of creation amid destruction. Imagine witnessing such an event up close, though not too close. No nearby planet could survive it intact. From a safe vantage point, you would first see nothing unusual, perhaps just two faint stars spiraling faster and faster around each other. Then, almost without warning, an overwhelming flash, a burst of gamma rays invisible to your eyes but lethal in intensity, and a powerful invisible ripple through space-time passing by. Immediately after, a roaring fireball of debris blossoms into view. In moments, it grows from the size of a city to the size of a planet and beyond, glowing first bluish-white, then rapidly shifting to crimson as it expands and cools. The entire spectacle unfolds and fades within a few weeks. It is a vision of both supreme violence and astonishing beauty, a cosmic fireworks show that marks the death of two stars and the birth of something new. For countless eons of the universe's history, such collisions came and went unobserved by any conscious being. They were nature's secret, spectacular fireworks, happening in distant galaxies and leaving behind only faint whispers. But recently, in our own time, we finally caught one in the act. One quiet August day in 2017, our detectors on Earth felt the subtle tremor of space-time from a neutron star collision, the very gravitational waves we've been imagining. It was as if the cosmos itself rang a bell, and for the first time, we were listening. Just seconds after that gravitational wave, chirp, rolled through our planet. A satellite picked up a brief flash of gamma rays from the same patch of sky. Alerts went out around the world. Within hours, dozens of telescopes had swiveled to find a new point of light in a galaxy. There it was, the telltale fading glow of a kilonova. Humanity had witnessed, for the first time, the full performance of a neutron star merger. We both heard it through gravitational waves and saw it in light, a cosmic event observed in stereo, providing stunning confirmation of what our theories had predicted. This watershed moment was a triumph of science and a wonder to behold. It proved that these quiet dancers in the dark end their lives in stupendous fashion, just as astronomers long expected. We watched as two neutron stars, after an ages-long spiral, met their spectacular end in a final flash. And yet, in that end was also a beginning, the birth of new elements and the emergence of a new cosmic object from the wreckage. When two neutron stars collide, they do not simply disappear, they transform. They leave behind debris and often a new ultra-dense remnant. To understand the full significance of such an event, we must look at its aftermath and legacy. In the wake of the neutron stars' violent union, something remarkable has happened. A cosmic act of alchemy. The debris flung out by the kilonova explosion is full of newly forged atomic nuclei. These are heavy elements, born in the flash of the neutron star collision. In those fleeting moments of unimaginable pressure and neutron bombardment, atomic nuclei captured free neutrons and built themselves into some of the heaviest atoms in existence. Elements that a normal star could never produce were synthesized in droves during the merger's aftermath. The expanding cloud of material is like an enchanted forge, transmuting matter into treasure. But the treasures it creates are not mythic gold from lead. They are real gold from energy and neutrons, along with platinum, uranium, and a host of other heavy metals. It truly is cosmic alchemy. The stars have transmuted their shattered substance into a trove of new elements. As the glowing remnants of the kilonova fade into space, they carry with them these riches. Consider what that means. All around that once quiet corner of a galaxy, new atoms are now wandering free. Atoms that did not exist just a short time before. Among them may be gold and silver and platinum, precious metals now floating as microscopic dust. There will also be more exotic species, the bluish element tellurium, the noble gas xenon, rare earth elements like neodymium, and radioactive elements such as uranium and thorium. Dozens upon dozens of heavy elements, some stable, some destined to decay over years or millennia, are flung out into interstellar space. It's a veritable cosmic treasure cloud, expanding and mixing with the interstellar medium of the galaxy. The quantities involved defy easy imagination. Astronomers estimate that a single neutron star merger can produce an almost inconceivable mass of heavy elements, far beyond what any normal star could scatter. One such collision, observed in our cosmic neighborhood, was calculated to forge elements totaling thousands of times the mass of Earth. To focus on just two famous examples, gold and platinum, the yield was on the order of 10 Earth masses combined. Picture that. An amount of gold and platinum equal to 10 planet Earths in mass, scattered into space by one celestial event. It's an amount far beyond the total reserves of these metals on our planet, created in an instant and cast across light years. So when we talk about gold being precious or rare on Earth, we're really noting its local scarcity. In the cosmos, gold is made in grand, furious furnaces like this and flung out as dust to seed future worlds. Indeed, much of the gold in your jewelry and the platinum in our electronics, even elements like iodine that our bodies need, or uranium that powers reactors, likely owe their existence to collisions of neutron stars. Long before our Sun formed, some ancient pair of neutron stars in the Milky Way must have merged, spewing their newly made heavy elements into space. That debris mixed into the cloud of gas and dust that eventually condensed to form our solar system. Thus, the very atoms heavier than iron in the Earth's crust and in our bodies have an ancestry that traces back to these cataclysmic stellar events. In a literal sense, we carry the ashes of long-dead neutron stars within us. This realization is both humbling and wondrous. In the aftermath of destruction comes creation. The violent demise of two stars becomes the birth moment for countless new building blocks of nature. Through such processes, the universe enriches itself. Over cosmic timescales, as neutron stars merge here and there, galaxies become sprinkled with more and more heavy elements. These collisions are relatively rare, perhaps only once in tens of thousands of years in a galaxy like our own. But the universe is vast and old, and time is on its side. Even rare events add up. And each merger is so prodigious in output that just a few over the eons suffice to supply a significant share of the heavy elements we find around us. In fact, scientists now believe that roughly half of all the elements heavier than iron, things like silver, gold, iodine, xenon, and lead, are forged in neutron star mergers. The rest come from other cosmic foundries, such as supernovae, but these particular collisions fill in a crucial chapter of the universe's chemical story, helping to solve the puzzle of where the heaviest elements originate. While the dispersing cloud of the kilonova's ejecta drifts outward and cools, at the center of the chaos, a new object has taken form. The two neutron stars have become one. But what exactly is this new remnant? Often, the combined mass of the two stars is so great that nothing can support it against gravity. In those cases, the merged core collapses further into a black hole, perhaps the smallest newborn black hole the universe has seen in that moment. This newborn black hole would swallow some of the surrounding material almost immediately. In our 2017 observed collision, for instance, evidence suggested that a black hole formed after the merger, likely one of the lightest black holes ever known. If so, it sits quietly now where two neutron stars once danced, its presence betrayed only by a fading afterglow of hot matter that briefly swirled around it before falling in. There is another possibility too. If the combined mass of the merger does not greatly exceed the limits for a neutron star, the two might, at least temporarily, form a single extremely massive neutron star rather than a black hole. Such an object would be like a neutron star on steroids, incredibly hot, rapidly spinning, and with a magnetic field far beyond that of a typical neutron star. It could even be a magnetar, a neutron star known for an outrageously powerful magnetic field. This hypermassive neutron star might survive for a short time, seconds, hours, or longer, furiously shedding energy. It could even emit extra radiation or energetic winds that shape the kilonova's aftermath, perhaps making the explosion brighter or altering its light in subtle ways. However, if it cannot shed enough energy and mass, gravity will eventually win. The overheated object will collapse into a black hole after all, once it cools and slows down sufficiently. In either scenario, whether a black hole forms immediately or a heavy neutron star hangs on briefly, the original neutron stars as separate entities are gone forever. They have merged into a single remnant born from their destruction. What's left, then, after the fire has dimmed? We have a rapidly expanding cloud of debris, enriched with heavy elements, destined to wander the galaxy. And we have in the center either a nascent black hole, hidden behind a veil of its own gravity, or perhaps for a while, a highly energetic neutron star that will soon collapse. If it's a black hole, it might be ringed by a thinning disk of material, the last bits of the merger's matter still funneling in. That disk would have helped power the initial gamma-ray burst jets. But now, shortly after the event, much of it has been devoured or flung away. All that remains of the brilliant kilonova is a cooling nebula, which within weeks grows too faint to detect. and eventually will disperse entirely. Yet the story does not end there. The products of this collision, both the matter and the gravitational waves, will continue to influence the cosmos far and wide. The gravitational wave energy travels onward, spreading out through the universe, perhaps one day, to gently jiggle the fabric of spacetime in some distant solar system. And the matter, those precious atoms, will drift for ages. Some of it will coalesce into tiny dust grains, riding the interstellar currents of the galaxy. Over millions of years, that material may mix into giant molecular clouds, the cradles of new stars and planets. Perhaps, eons from now, those atoms will find themselves incorporated into the soil of an alien world, or into the bloodstream of some living creatures yet to evolve, or glittering in the rings of a distant planet. This is the ultimate legacy of a neutron-star collision. It's both an ending and a beginning. Two stellar remnants end their lonely journey in a final flash. But from their demise, the galaxy is enriched with new matter and a new compact object. A black hole, or a massive neutron star, is born. The elements created will long outlast the fireworks that birthed them, seeding future cosmic generations. In this way, the universe continually recycles the ashes of dead stars into the ingredients for new ones. The quiet behemoths had one last, spectacular outburst, and in fading, they whispered into the cosmos the materials that will become part of the next chapters of creation. After the clangor of the collision and its aftermath, what remains might seem almost anticlimactic. A dark, silent remnant, and a cooling cloud dissipating into nothingness. But hidden in that outcome is a sense of connection. The universe has woven this single violent event into the tapestry of countless others through those dispersed atoms. And for us, it ties something as personal as the gold of a wedding ring, or as essential as iodine in our bodies, to something as distant and dramatic as two neutron stars colliding. The aftermath underscores how even the most cataclysmic cosmic episodes eventually translate into the gentle materials of life and worlds. In the grand scheme, the violence gives way to silence again. The black hole, if one formed, emits no light. The hot debris cools to invisibility. Space grows quiet in that region. The show is over, and the dancers have left the stage. But the echoes of their performance persist in the universe's memory, written in gravitational waves that have long since passed us by, and in atoms now adrift, awaiting their chance to become parts of new worlds. The cosmic choreography of binary neutron stars and the cosmic echoes of their collisions have taken us on a journey, from a gentle orbital dance to a supreme conflagration, and finally to an enriched quiet. Yet our exploration of neutron stars is not complete. These stellar remnants have more to tell us, not only in their explosive finales, but also in their steady, cryptic signals that endure over millennia. Even as the debris of one collision disperses, elsewhere in the universe, other neutron stars continue their peaceful rotation. It is to those steady cosmic timekeepers and guides, the pulsars, that we now turn our attention, to discover how these quiet behemoths continue to influence and illuminate the cosmos long after their spectacular births and violent collisions. We continue our journey through the cosmos, moving beyond familiar stars and planets. Now, a new chapter unfolds as the universe itself grows quiet. We drift slowly, but inexorably, into the long twilight of the universe. Around us, the brilliant galaxies we once knew soften and dim. What was once a sky bright with fiery stars becomes a gentle expanse of fading light. This is no sudden change, but a gradual, eternal evening, bathed in the serene hush of cosmic twilight. In the long twilight of time, the bright stars begin to fade. Our sun, once a burning beacon, ages and cools over eons. It will one day fade to a dim ember, joined by countless other stars that also simmer quietly. White dwarfs dot the void, glowing softly from the last embers of fusion long after new star birth has ceased. The great gas clouds that once birthed new suns have thinned and dissipated. The cosmos keeps its light, but all the fires of creation are slowly running down, leaving a gentle glow in their wake. Galaxies drift apart on the winds of cosmic expansion, carried by unseen forces of dark energy. Each is a lonely island in vast emptiness. The night sky grows emptier as these distant island galaxies recede beyond view. Space itself stretches, and emptiness spreads between the remnants of light. This great distance can feel cold and isolating. But even in this profound quiet, a serene beauty unfolds across the horizon. Among the dying stars, the smallest lights still flicker for a while longer. Tiny red dwarfs, the dimmest of stars, burn with patient endurance. They whisper out light for trillions of years, their quiet existence a soft comfort in the darkness. Even in this deep cosmic evening, pockets of gentle light remain. These humble stars serve as campfires in the night, warming the surrounding darkness with their steady glow. In their presence, the night does not feel entirely empty. The cosmic microwave background, the very afterglow of creation, has been cooling and fading for eons. Once it filled the sky with the warmth of beginnings, but now it is but a faint echo. This ancient, gentle glow has become nearly silent, like the last note of a lullaby fading into memory. It reminds us that even the universe itself has been a long moment of tender light. Now, as this primordial light grows ever cooler, it too relinquishes its watch. Occasional murmurs still ripple through this dark expanse. Black holes, those tremendous anchors of shadow, might leak out tiny pulses of energy in their final decay. A stray cosmic ray, or a fading supernova remnant, may kindle a momentary spark. But such events are rare, and each is gentle, more like a flicker than a flash. These final whispers of energy are hushed, embracing the silence rather than breaking it. In the far future, the boundary between day and night dissolves into one vast dusk. Time loses its normal rhythm in this deep age. Years can feel like single moments, and eons like entire lifetimes. We drift in a twilight that never ends or begins. Yet even as light fades, every glimmer of a star or distant galaxy feels precious. In this endless evening, we find a strange kind of comfort. The slow passage of time feels gentle and unhurried, as if the universe itself is breathing softly. The emptiness around us is profound, but it holds its own kind of beauty. Darkness is not harsh here. It is a soft veil covering everything. Any light that remains shines brighter for being rare. A single distant star becomes a beacon of hope, its pale blue or golden glow touched with significance. We realize that even the faintest lights cast far shadows in such quiet. In this gentle twilight, Every ounce of light counts. Though the cosmos has largely grown quiet, there is still a deep warmth in its memory. Our souls remember the heat of the universe, when stars burned freely and planets thrived. Even now, tiny smoulderings of that heat linger in the interstellar gas and cooling stellar corpses. It's as if the universe sighs, content, even as it settles into rest. In feeling that memory of warmth, we know the cosmos has not abandoned us. Slowly, the familiar patterns of the night sky have drifted away. Constellations we once knew have faded, replaced by ghostly apparitions of long-lost stars. This ever-changing canvas suggests that even silence is dynamic. Only something deeply peaceful could create such subtle change. We watch these quiet transformations and find them gentle. They happen beyond sight, but they remind us that the universe still turns, albeit with grace and tranquility. At times, our thoughts wander through all that has passed. We remember how vibrant the universe once was, filled with brilliant light and life. Those memories comfort us like a blanket in the night. Though we cannot hold that brightness any longer, we carry it in our hearts. This recollection is like an ancient lullaby, a melody that lingers after the song has ended. In these gentle memories, the cosmos remains alive to us. Though the light of stars fades, the universe continues to teach us gently. It teaches us acceptance, tranquility, and hope. In this eternal night, we learn to sleep peacefully beneath the silent sky. We trust that even if the heavens are dark now, light will come again in another form. For now, the universe is resting, and we rest with it, wrapped in its calm embrace. In the deepening silence, any souls left in the universe stand under the vast night sky as gentle watchers, perhaps on a distant world far from here, or right here on our own quiet planet. A few observers remain. They look up at the heavens in wonder, feeling both small and connected. The sky may feel empty, but those patient eyes find comfort in the cosmic stillness. Even alone, a watcher's curiosity kindles a soft light against the dark expanse. In their silent vigil, the universe seems closer, as if sharing its ancient stories with just these humble listeners. In the hush of this deep solitude, each watcher's heart becomes an open ear. They lean closer to the cosmos and listen with their souls to the universe's gentle breathing. Memories of brighter days linger in the air like soft notes of a distant song. Once familiar constellations have changed, yet every star or galaxy they see feels like an old friend now at rest. Here, under the quiet expanse, there is a sense of belonging in simply being present. Perhaps one last voyager drifts in the dark gulf between stars, soul humming with quiet awe. Or maybe no life remains except the quiet hope in the human heart, still beating as it did beneath busy skies. Either way, if eyes remain open to the night, they are greeted with a profound peace. To behold the cosmos in this gentle stillness is to feel both loneliness and togetherness at once. We become not just observers, but part of the cosmic story unfolding in silence. For the watchers, solitude becomes companionship. They fill the emptiness with memories and quiet conversation. Sometimes they speak softly to the night sky, And though no answer comes, the act itself offers comfort. In this calm, their thoughts become companions, the wonder of ancient supernovas, the shape of distant worlds. The absence of noise means every feeling, every memory resonates more deeply. Even alone, they never feel truly lonely, for the universe is listening in its vast, hushed way. Imagine sitting on a dark, silent rock, or drifting in a slow-moving ship, gazing up. In the great quiet, you might feel as though you're the last storyteller, cherishing the tales of old constellations. And as you watch, new silent stories are born. Each heartbeat, each breath, becomes part of the cosmos's rhythm. In the solitude, we hear the whispers of our own hearts, as clearly as we hear the distant hum of galaxies. In this solitude, the watchers realize a gentle truth. To be alone under the night is also to be connected to everything. Each thought ripples outward, joining the silent chorus of existence. Perhaps in this quiet, they even sense the echoes of distant hearts, the whispered dreams of those who once gazed up as they do now. They are part of an unbroken chain of wonder, and in that chain they find profound comfort. We imagine someone softly running a hand along cool metal controls, or gripping a worn blanket by campfire light. They look at the dark and trace old constellations in their memory. In each tiny personal gesture, there is a cosmic significance, as if the silence itself listens. No words are needed. Even the slightest sign of presence dances with the stars. In this wordless conversation, the watchers and the universe embrace each other. In this hushed moment, the relationship between life and matter feels undeniable. We see clearly now that all living things, from the tiniest microbe to the grandest star, share one fate: transformation. We, who once learned to build civilizations beneath the bright sky, now find comfort in returning to the cosmic cycle. What we call life and death are simply two sides of the same cosmic current. In each of us burns a star's legacy, and in our final quiet, that legacy drifts out to become something new. Alone in the silent universe, every simple moment feels profound. We hold a universe within us, stardust in our veins, history in our minds, dreams whispered into the void. Our thoughts, once as fleeting as breath, flow now like currents in a vast ocean of time. This sky teaches us that even as individuals, we are never truly gone. The energy of our being merges into the fabric of space, echoing eternity back at us. We think of all the people and creatures who once gazed at the heavens. Each one, in their time, was a watcher too. Their hopes, their memories, their understanding, all of it is scattered through time. Now, looking upon the same sky that once awed them, we feel connected to countless generations. This lineage of wonder binds us together, even as individual stories fade. Perhaps in this quiet eternity, our thoughts become part of the cosmic memory. Though no voice remembers us, the universe holds our echoes in its gentle hum. If someday, in a far future dawn, there were beings who would listen, they would find traces of us in the stardust. In that thought, we find solace. Nothing is ever truly gone. Energy persists, and so do ideas. Somewhere, somehow, our presence lingers. In this everlasting moment, there is no rush. Time slows to a slow, harmonious pulse. The silence envelops us like a lullaby, guiding thoughts into soft dreams of cosmic wonder. We no longer need to hurry or strive. Here, everything can simply be. Beneath these quiet stars, peace is not a distant dream, but a living presence. In awe, we watch and listen to the universe's serene heartbeat. We stand in awe under the silent sky. The darkness that surrounds us feels gentle, like a soft blanket of peace. The stars and galaxies we see are few, but each is a precious flicker in the vast quiet. They do not shout their presence. Instead, they glow softly, modest and eternal. In the stillness of this final night, we feel small, yet deeply connected. This boundless silence is not empty. It is filled with the memory of all that once was. We listen to the gentle hum of the universe, a soundless song of creation and rest. Every breath we take honors the calm wisdom of the cosmos. Gratitude flows through us. We owe the quiet cosmos a silent thank you for its wisdom. For every question it soothed and every mystery it shared, we are grateful. Here, in the warmth of that gratitude, we find acceptance. We are at home under the silent sky, our journey mirrored in its eternal calm. As our eyes gently close, we carry forward its serene hush in our hearts, sleeping peacefully beneath the endless sky.